2402 really is about beams themselves, right? We have lots of other steel elements, so we're going to cover that from a really high level as well, and just some general expectations on what you might see on the job site. So here's our basic outline. I do intend to spend the first hour kind of getting through the very basics of a steel bridge, right? Because we don't use a ton of them in Minnesota, but I think it's important to understand a little bit of the background as to when you do encounter these, why they're out there. And then we'll spend a fair bit of time on that field inspection piece of this. So that's what we'll look at. Take a break roughly every hour because this one does consume the entire morning. And then Steve Miller will pick up this afternoon with steel bridge painting. So general references, got your course manual obviously, and we have tried to get the course manual in sync with this presentation if you're trying to follow along. I will note that there probably are a few discrepancies in there, just FYI. Bridge Construction Manual is a great resource that will hopefully someday get updated, but there's still a lot of good content in there. Standard specifications. One thing I do want to point out with the 2020 spec book, we did break out a few things, expansion joints, certain types of bearings, metal railings, all used to fall under 2402. They now have their own sections, which has been a good thing. A couple other items that are also made of metal that we should be aware of that could reference back to 2402. And then just a brief overview of items that are scheduled materials control that fall under that 2402 item. Just a reference list here. So why would we choose to use a steel superstructure, steel beams? We are predominantly a pre-stressed concrete beam state. Generally, with a steel structure, you can have shallower and lighter structures than compared to concrete. This, in turn, gives us smaller foundations, which can be a really good thing if we're trying to minimize excavations, and they can reduce the cost of a grade raise of everything coming in, right? So your bridge may cost more because generally steel has a more costly upfront cost. But as a total project, you may be able to save a fair bit of money if you have to do a significant grade raise. Longer span capabilities, and I'll highlight this in another slide here. And then it's really adaptable to unique geometric constraints. So pre-stressed beam has to be a straight element. There's nothing that we can do to change that. With steel, we can do curves, we can do rolls, do a lot of different things that can help us get around challenging roadway geometrics. So let's look at this a little bit. Shallower sections. So we have these 2 points right here. Oftentimes the most force that your beams need to carry in a continuous span, and we'll talk about this in a moment, is right over a substructure. So in this case, we can use more depth right at up here and less depth in the span, which could have an advantage if you're trying to go over a roadway, right, meet your vertical clearance requirements. So steel is highly adaptable to these types of things where you can put the most material where you need it. We also can do very long spans. So this is your example bridge. There should be a supplemental package of plans, bridge 69129. This bridge is over 1,000 foot long bridge with a 480 foot center span. Really large span for a beam bridge. And then unique geometry. So if you look at this photo here, this is a plan view of a bridge in St. Paul that kind of looks like a left-handed mission. And so the red represents the edge of deck, the green represents the substructures. And so this is all one bridge. We were able to use steel to be able to bifurcate off of the main line and have this be one continuous structure that's all framed together. So it's very adaptable to these unique situations. Obviously this would be way easier to build on dirt, right, than trying to build a bridge floor, but steel helps us accomplish this. So why don't we use steel all the time? Again, it's initially more expensive compared to our typical pre-stressed girder bridge. It does require a paint system underneath the expansion joints at a minimum. And paint has a much lesser life cycle than what the beam itself does. Because generally out in their joints repaint every 20 to 30 years. And it can have longer lead times because with a steel beam, and we'll get into this a little bit later, the contractor is not going to buy any of the steel until everything's been detailed up through the shop drawing process and approval. So we'll talk about that because that can have project implications. there's your basic introduction. Let's get into the anatomy of a girder so that we can all speak the same terms. Now I'll use girder and beam kind of interchangeably. In Minnesota, generally, a girder is a welded up member. So we're taking a lot of individual plates and welding them together. Where a beam is an element that's all rolled out of a single piece of steel. Breaking down the beam or the girder, we have a top flange, a bottom flange, and a web vertical element that's going to connect the two. So that's your individual girder or beam line. These within a bridge are interconnected to one another using both the deck, but before the deck goes on, a diaphragm or a cross frame. And again, I'll use these interchangeably as well. Generally, we think of cross frames in this X or K configuration. Diaphragm tends to be a solid plate that goes between the two. These cross frames or diaphragms are connected to the girders using a transverse or intermediate stiffener. Those stiffeners are welded directly to the girders, where the cross frames or diaphragms in Minnesota are almost always bolted to them. So if we look at a photo of what this looks like versus a diagram, you can see that this is the 53 bridge having a ground splice, but we have our bottom flange, our top flange, lots of diaphragms or cross frames. Here's that intermediate stiffener. You can see the bolts getting ready to take a diaphragm. Longitudinal stiffener. This is unique to a very deep girder. We need that just to stabilize that web because it does want to get kind of spindly if we get too tall. And then a field splice. Pieces can only be shipped from the fabrication plants at a certain length, right, because of trucking limitations. So we have to have a way to bring these pieces together. And oftentimes we'll do that with a bolted field splice. And we'll talk about that more. So looking at this from plan view, you're going to see a lot of those same elements on your plan. We got designation for our field splice. You can see the girder lines or beam lines running across the page. We have intermediate stiffeners that have no diaphragms connected, and then we have other stiffeners with a diaphragm connected. Also on these plan views, you'll find what your bearing assembly type is designated to be. And in this case, you can see all of these X's. These are known as lateral braces, and that's to interconnect the two beams in a different plane. And so you can see here, as highlighted by this X and then this one next to it, instead of providing a vertical component as a diaphragm, we're providing a horizontal component. And oftentimes we're only putting these in for the stage before the deck gets put on. Because those girders, as they are subject to wind, they're going to want to wave back and forth. And this will stiffen it up and keep the system safe and stable. A couple other elements. At every substructure, you're going to have what's called a bearing stiffener. This is going to be a thicker plate that helps stabilize the beam as it takes all of the force that it's collected and moves it into the substructure. Oftentimes, we'll put jacking stiffeners to be able to do maintenance on the bearing in the future. Essentially, if you think about putting a little jack right here, all of that load has to go into the jack. And if we need a bearing stiffener to stabilize the beam, once that load moves over 2 to 3 feet, we also need to be able to stabilize it. So we'll put jacking stiffeners in. All of our substructure, all of our beams will bear on some sort of bearing assembly element, which you can see here. But between that element and the beam itself, we put what's called a sole plate, just to help with that interconnection. And this one's obviously sitting on up here. What does that look like again in a plan, an elevation view? You can see the jacking and bearing stiffeners called out here next to the bearing assembly type, and then detailed here in the elevation. This is just another example. So I talked about real briefly a continuous steel system. So let's take a step back and think about what that really means. So the photo here would be what's called a simple span. This is what all pre-stressed beams are in Minnesota, meaning that at your bearing points or at your substructure, there's going to be a physical break between the beam for the next span. And so when you have a simply supported span, as it's loaded, you're going to get tension, or a force that wants to pull something apart, developing in the bottom, or opposite of the load, I should say, and compression developing in the top. That's known as flexure. So for a simply supported span, you're only going to have this tension for for all intents and purposes, develop in the bottom. Now for steel, and this is partially why we can get away with oftentimes shallower sections, a continuous span, you don't have that break at a bearing point. Your beam continues right over the top of that bearing as one continuous piece. And because of this, you have tension that can occur in both the bottom and the top flange. And this is important to know because we have rules in our spec book around what can be done in the top flange tension zone that's often labeled as area A. So you can see we still have that smiley face out here between the two bearing points, but as you go over a new bearing point, it turns more into a frowny face, right? And the way I like to think about it is tension occurs opposite of your load. So if you have a truck sitting out here in the middle of the span, all of the weight of that truck has to get carried back through the beam to your substructure, right? So at your bearing point, you always have a load, right? But that load's just pointing upwards to hold the bridge up. Does that kind of make sense? So that's a simple way to think about where you're most likely to have tension in the beams when you're out in the field. Let's talk a little bit about materials. So our structural steel, we generally are using for beams a higher strength steel. So this is going to be 50, 70, or 100 KSI yield steel. For the most part, we're using all corrosion resistant or weathering steel on our beams. Other states do this differently, but Minnesota has taken the approach of a weathering steel system on most of our beams. It comes in a variety of shapes and sizes. MnDOT spec, if you want to dive into the material specs, this is where you're going to find a lot of that steel information. I will note that this 3306 is not a high strength steel. This is more of a standard grade. So if you're going to go by angles or channel sections off from a supplier, they're going to be subject to this lower strength steel. So we talked just briefly the difference between beams and girders. Beams generally are classified as rolled shapes. So they are one single piece of metal that's been heated up and set through a series of die rollers to make up these standardized shapes. So oftentimes we're using this for built-up elements, like diaphragms. We can get beams up to about 44 inches. They do produce beams that are larger than this, we just don't see them in the transportation industry. But again, often used for diaphragms or miscellaneous elements. This is just a kind of an idea, and it's a really cool process to see here, just YouTube it, but what they do, the steel mills produce what's called a billet, and the billet, I believe, is a 12-inch by 12-inch square that's usually 40 to 60 feet long. And to make these shapes, they heat that billet up, and they send it through a series of die rollers. And so you can see this one is working its way from the left to the right. You can see how we have a rougher section. As it gets more refined, it gets into that final piece. Now they do this at a really quick rate. I worked for Nucor for just a little bit, and I got to tour a couple of their facilities, and I believe they were making angles, and by the end of that line, that angle was going, I think, at about 50 miles an hour through these dies. So it is very fast process once they get it heated up. But kind of neat if you're interested. So again, we're going to find these mostly in our diaphragms and our cross frames. So you can see all these different things that have been labeled here. So our welded girders, our top and our bottom flanges and our web are all made up of flat plates. And this allows us to go to depths greater than 44 inches. The tallest section I've been involved with in Minnesota has been 15 feet. So you can get big chunks of steel that we can shape into a variety of different depths. So they're going to come out as these flat plates. You can see it's situated in the yard. And then we can optimize where we need more thickness because you can weld these together, where that rolled shape is just one consistent shape and one consistent thickness. Fasteners, so we showed the picture of the bolted field splice. This is a longer bolt, but this is our typical fastener system. So we have type 1 and type 3. Our type 3 we're going to use when we have a painted girder, because this is going to be a mechanically galvanized system made of weathering steel. And that's what's shown here is this type 3. Our type 1 is just going to be an alloyed steel. It may or may not be galvanized. Generally, a similar strength it has the same minimum strength requirements. For the most part, in structural bolting, we are only going to be using 7/8 or 1 inch diameter bolts. But 7/8 is by far the most common. That fastener system is completed with nuts and washers. You see that we have a standardized washer. This is your typical hardened washer that you're used to seeing in like a hardware store, for instance. But then we're also going to have a special washer that we'll talk about on the next slide. Our nuts, in this case, for a fastener system to behave properly, it has to be well lubricated. And so you can see here that these nuts have this blue dye, which just indicates that they have a coat of lubrication that's going to be used in the system. We're going to dive way into this in the second and third hour today. We have these special washers that MnDOT uses called direct tension indicator washers, or DTIs. And we're going to dive way into these, but just really take away right now that we're going to have these special washers with protrusions on them. And those protrusions, we're going to work on crushing as we tighten the fastener to know that it's tightened to the level that we need it at. Oftentimes, a lot of questions about how these fastener assemblies work. And so you can see we have our structural bolt joining the 2 plies of steel. You're going to have your hardened washer on the back side here with a nut, and your DTI is going to be placed underneath the head. We generally try to have that DTI opposite of the turned element. Generally trying to turn the nut when possible. But again, we'll dive way into this, but just to give you a little bit of a preview. With our fasteners, an important note that's been added to the spec book within the last 5 years is everything has to have row cap testing. And this just looks at the rotational capacity to make sure that the bolts are going to perform the way that they've been designed. Biggest takeaway for you folks is that if there's no documentation that this has happened and should happen by the supplier, it's got to be performed in the field before it gets incorporated into the structure. This is a long, onerous process, and so it's really important to get ahead on this and make sure that it's been done prior to the bolts being shipped to site. So if it's not, contact the bridge office. We can help you through this. Another element is shear connectors. So if you think of a pre-stressed beam and you got the hoop bars coming out of the top, with steel beams, we use shear connectors to accomplish the same thing, join the deck to the beam. But because of OSHA, these have to be field installed. And so these are just studs that get welded to the top once you have all of your decking falsework in place. And then welds. Minnesota is generally a no field weld state, with a couple of exceptions. Piling, expansion joints are the 2 main ones where we permit field welding. Very, very rarely are you going to see any sort of field welding on a structural beam, but if you do, it needs to be accompanied by a weld procedure specification, a WPS. Has to be performed by an AWS certified welder that's kept up on their continuity records. And we talk a lot about field welding in the piling section. We've developed a really nice checklist for folks too to make sure that the qualifications that are being presented to you are accurate and meeting the needs of the project. That's your basics of steel design, or steel bridges. Is there any questions on that? Awesome. Plans and shop drawings. So steel elements, I should say, are unique. Every one of you has a plan in front of you, right? So you have 2. You have a steel plan and a concrete plan. This plan is not how the girders are fabricated. Girders are fabricated using shop drawings. So let's dive into what the difference is between these 2. Your plan drawings are going to have a lot of structural steel notes. Most of these notes are geared or directive towards the fabricator on what they're supposed to be doing, different conditions they have to meet. But there's going to be some useful information that relates to the erection of these beams that you're going to have to understand as a field inspector. So open up your plan for bridge 69-129. I'd like for somebody to tell me what sheet the structural steel notes are on. What sheet number? 7. Everybody find that? The left side takes up most of the height of the page. We'll be referring back to this, so just make sure you understand where this is in the plan. Is there anybody that has not found it? Okay. So shop drawings versus plan drawings. The plan drawings are prepared by the engineer of record to provide the basic element sizes, some of the details, and a lot of the geometric features. What these don't do is provide a detailed guide for how to assemble every single piece. And that's where the shop drawings kick in. Once the contract has been awarded, and you have a general contractor that has an agreement with a fabrication facility, the shop drawing process is going to commence. And what these really look like is it's a very detailed breakdown of every single piece of steel that's going to be incorporated into that element. That's exact dimensions, sizes, a bolting list, blocking diagram. We have to hammer these beams, which we'll talk about. Match markings, right? You got several pieces that are going to be joined together, and oftentimes they're drilled in place, so they're only going to fit with the piece that it was drilled with, right? And sometimes field erection plans. So this is a separate document that's produced after the contract has been awarded. But once it's been released, or once it's been accepted into the project, it becomes part of your contract, and you need to incorporate this into field use. So this is something that's going to come later. It's probably the biggest piece. We don't just use these for steel beams. You're going to have shop drawings produced for bearings, ornamental metal railing, expansion joints, T1 railing, a lot of different steel elements, right? Oftentimes it's going to be important for you as an inspector to go in and at a bare minimum look at the general notes for any one of these shop drawings, because they may have special instructions that relate to field installation. So the example here, we've got anchor rods. So for our normal ornamental railing, you get to drill in the anchor rods, right? It makes fit up a lot easier in the field. For our T1 rail, because that's a structural element that has to take a much higher load, a traffic collision, those anchor rods have to be cast in place, and you have to fit the rail in place. So it's important to be referring to those shop drawings instead of the plan drawings, because they're going to have more refined dimensions for how to actually place those anchor rods in the right spot. Grout tubes, so if you're using high load bearings, those also we can't drill in our anchorage after the fact. We're going to cast those in. And to provide flexibility, we put grout tubes in and fill those. Once we stuff the anchor rod in there, we fill those tubes back up with grout. It's going to be really important to refer to your shop drawings so that those grout tubes get placed in the right location when they cast your substructure. As I've been involved with a job where they're in the wrong spot, and you're talking about now taking a 6-inch core on the top of the pier cap and trying to miss steel. It's very challenging. So these are things where you're going to need to, as an inspector, go to the shop drawings to verify that things are in the right spot. More recent example that's probably going to be something more folks will see. Our ornamental railings now have to be continuously grounded for electrical continuity. So basically, if you think about, I don't know if anybody's been to the zoo recently, they've got the new monorail trail, and when people walk, they generate a ton of static electricity. You touch the railing to hold you on, and you get zapped. And so we have to provide this electrical continuity now to prevent something like that from happening. Now on our structures, it's more likely going to be stray current from high wires or if there's utilities attached to the bridge. But there's now special installation instructions on how to create that continuity in these rails that the contractor and yourselves need to be aware of. So fabricator is supposed to submit the shop drawings directly to the fabrication methods engineer. This oftentimes creates confusion, but the idea is the fabricator is really working back and forth with the engineer to resolve issues right away. And this is all happening outside of the project site. So shop drawings should be submitted directly. They're ultimately going to be accepted by that fab methods engineer, but that acceptance does not relieve the contractor from things like making sure everything's accurate in there. The review is just for general compliance in the contract, not checking all of the dimensions. Contractor still is going to be ultimately responsible for fitting all of the members together, and then adherence to all of the other specifications that are involved. So what do these look like? Let's go through a couple sample plan sheets. Here's would be a typical plan view. This looks a lot like in your plans, right? This is going to provide out the basic dimensions, but what you'll note here, and it's probably a little bit hard to see, every one of these diaphragms has a label to them. Beams have a label, all of these lateral braces. So those are unique piece names. On this bridge, because of the configuration of it, they were able to repeat a lot of the same diaphragm configurations and make things fit. If you have a unique skew, or perhaps maybe your girders are bifurcating away from one another, every one of these diaphragms might have a unique name. And that's important because that unique name gets stamped on that element, so that when it shows up in the field, you can refer back to this plan and know exactly where it's supposed to be. That will not be in the plan set that you have in front of you. Hence the need for a shop drawing, right? Because every one of these pieces can be unique. Here's a list of your sheets. For your example bridge right here, I believe the shop drawings are about a 500-page plan set. And that's just to fabricate the beams and the cross frames. So here would be your typical layout. You can see a lot of different elements go into making your bridge system as a whole. You got a whole sheet just dedicated to the bolts that are required to be shipped to the job. An important piece with any job, especially if you have bolted field splices, is understanding how to read this bolt shipping list. So in your contract plans, you're not going to find the length of the bolts that are required to make your field splices. The length, depending on the top flange, the bottom flange, and the web, you might have 3 different lengths, or potentially 6 different lengths if the steel thicknesses change from one side of the splice to the other. So it's important to know where the shipping bolt list is, so that you can start to get some of those details. So in this case, in field splice number 1, this is going to be your top flange, your web splice, and your bottom flange. It's going to give you the number of bolts. You can see that the bolt length varies depending on which element you're in. And another important piece is looking at this washer code. So down here, washer code 2 tells us that we have to have 2 hardened washers, not just 1. So this is in addition to the DTI that we talked about. I emphasize this because I was on a job one time where the iron workers forgot to put in that second washer. Nobody caught it for a couple days, but once we did, it resulted in replacing about 1,000 bolts. Bolts at that point were about, I think, $7.50, $8 a bolt. So, it's contractor's responsibility. We're going to own the time behind that generally, right? And so it's just good practice to dig into this, understand if that's something that's needed or not, because it's a very easy question to ask before the work gets started, right? It was a really big argument to get them to go back up there and replace it, even though it's in the contract. So just an FYI, that's a good sheet to refer to. These are also going to have camber diagrams. So most of our roadways are not perfectly flat, right? Oftentimes they have some sort of vertical profile to them. And so our steel beams, we will cut that profile into them so that once all the load goes on them, they match the deck riding surface, or at least close. So it's known as camber. So we have to cut all of that into these plates. You can't just naturally bend them that way. So you'll have camber diagrams. This can be important if the contractor is going to be doing ground splicing, to understand how they're going to have to situate things on the ground to match that shape, because otherwise they won't get the bolts to fit. So that's your camber diagrams. Any questions? Is there any questions specifically about the difference between a plan drawing and a shop drawing? Which one's more detailed, the plan or the shop? The shop. So, once the shop drawings have been approved, the fabricator is going to work on creating these elements. And there's a whole series of inspections, quality control, quality assurance that has to take place before those elements are ever permitted to leave that facility. So we cover this in two different areas of the spec work, because we have the work that you folks are going to be tasked with out in the field versus all of this work that has to happen in the shop. And so sometimes this gets a little bit confusing for folks. Who is the engineer when you're in these different parts of the spec book? So 2471 covers the fabrication process of any steel element. These are, when these products are being fabricated, in that chapter, the engineer is going to either be the engineer of record or your structural metals fabrication specialist. Because we want that interaction to happen between those folks. Once the products have been tagged and are approved to leave the facility, they move into 2402. That's where you folks are going to be involved, right? That's the field portion where we're going to actually erect these elements and install them on the bridge. And so the engineer refers back to the project engineer, project supervisor. Does that make sense? Oftentimes that gets a little bit confusing. Okay. Work, any type of metal element on the bridge is supposed to be fabricated by an approved supplier. So this doesn't include things like piling, right? That's bought from a supplier that just mass produces it. I'm talking about elements that are actually fabricated out of multiple pieces brought together. So they have, this work has to be performed by an approved supplier. This is similar to an approved products list type of thing, right? We have certain companies that can perform certain levels of work. So these approved suppliers are going to go ahead and fabricate these beams. So let's take a pictorial tour of what this might look like. Shop drawings have been approved. The steel order goes in. Generally, it takes 6 to 8 weeks to get this material to the fabricator's facility, depending on rolling schedules, plate sizes, things like that. So the fabricator is going to stockpile this out in their yard. These steel fabrication facilities, especially if they're doing girders, are several acres, because they have to have a lot of area to sometimes make 180-foot pieces of steel, right? So they're going to stockpile it, they're going to label it, figure out what they need, and then they're going to start preparing things. So they may, these flanges right here may have been cut out of these larger slabs of steel, right? Especially if they're curved, because they have to cut that curvature to the top. So they'll prepare the flanges. Here you can see they're getting ready. It's hard to see in this picture, but this piece of steel is thicker than this piece of steel. And so we're going to bring them, make them into one continuous piece. They've got to be welded together. So they will come in, and I know this picture is blurry, but they're going to put more or less a chamfer in here to be able to prepare for the weld. We're going to start filling that up with weld. You can see here's that thicker piece versus the thinner piece. This is an automated welding process when they're going to go back and forth and slowly fill up that joint to make a continuous joint weld. Does anybody know why these extra little chunks of angle are stubbed onto the beam? Do we see that typically out in the field? Anybody know why that's there? Anybody a welder?
Here we are.
Right idea. Makes it stronger. Why though? Yeah. So your porous quality weld is when you have to change directions. And so we want that poor quality weld not to be in our girders, right? Because when you get things like pore fusion, hydrogen bubbles, things like that, that can lead to long-term issues and ultimately make the steel crack. And so we have, these are called runout tabs. They're simply there to let that transition happen outside of the girder while we turn back around to make a multi-pass weld. Because this is probably, I mean, I'm guessing on thickness, this is probably a 7 or 8 pass weld, just to make. So these will get ground up and removed by the fabricator once the weld's been tested. Here's that grinding between passes to clean up any slag. Again, looks for that high quality weld. So we have our flanges made. Now we need to attach it to the web. Now remember, I said these can be up to 15 feet tall, which can be a really hard thing to support. So most of the girders are fabricated on their side like this, unless they have a really significant horizontal curvature to them. So they're going to lay that slab out. They'll support. You can kind of see these yellow beams down here are going to support both the web and these flanges. And the nice thing about laying these on their sides is that, again, we can go with an automated welding process. Have just a nice traveling welder go along and lay that bead of fillet weld for however many thousand feet it needs to go. Now you'll notice in this, we have those transverse stiffeners, right? None of those have been installed yet. And that's to allow for this automated welding process, so that you can have that weld traveler keep going along like the bead. So we'll go ahead, put that weld down, and then that's where we're going to start fitting the stiffeners. Now these stiffeners are detailed to be a very tight fit. And so based on the shop drawings, these elements will get cut to within a 1/16 of an inch. Generally, they're cut ever so slightly longer, and because of that, oftentimes they'll have to go in and put a jack to slightly separate those flanges, drop your stiffener in, let that pressure off and weld it into place, because we want these to be that tight of a fit. Once we have all the welding done, we go into our bolt hole forming. So this is where, as an inspector, you're going to need to go into the structural steel notes and understand what the forming operation was. And we'll really hit on this later, but that's going to be very dependent on how certain things have to happen during erection. So let's talk a little bit about the bolt forming. We have line assembly and full assembly. So our line assembly is where your diaphragms, diaphragm stiffeners, lateral bracing, other connecting plates are going to be drilled with an oversized hole. An oversized hole, for the easiest way to remember it, it's going to be 3/16 larger than your bolt diameter. You have a little bit more slop essentially in that hole. For our field splices in a line assembly, they're going to be drilled with a standard size hole. The standard size hole is a 1/16 of an inch larger. I know that doesn't seem like a lot, but when you're in the field, that's a lot of wiggle room. That's 16 versus 3/16. Right? So this is important to understand because you can start to appreciate what some of these tolerances are, especially as I show you some more pictures. So our field splices are always going to be a 1/16 of an inch oversized. And then when we have line assembly, you're going to have oversized holes. So here's line assembly. It's quite literally bringing the girders into alignment and starting to drill these holes. Typically what fabricators do is their field splice plates, so this outer plate is going to be drilled in some sort of CNC process, pretty precision. But then they're going to come through and with a couple select holes started to hold this in place, they're going to drill into the girder through the steel. So this is drilled literally in place, meaning that only these pieces are going to fit together. Now I highlight this because I was on a project once when they ship these splices, not all the holes are stuffed. Usually it's just a handful of them to keep them on there. The fabricator put the wrong splice plate on. That's easy to do when you're only stuffing 8 of the 48 holes. Contractor didn't check the match markings, got it up in the air. I think this splice had about 200 bolts in it total. We got about half of them in and realized there's no way this is going to fit. And that's when somebody looked at the match marking and realized it was the wrong piece. So these are, even though it's a CNC process, CNC is not that perfect when you start to get to this level of precision and this many bolts. So it is important to check that kind of stuff. Why we emphasize that we're drilling through the blank. So with line assembly though, because we're using oversized holes, these can be drilled elsewhere in the shop. So here you can see they're putting a template together, they're drilling these holes, they're not drilling them through the stiffener in the same location, because we're going to have that 3/16 of an inch oversized in every hole that these are going to connect to. So there's a lot more slop. They can be interchanged if their match markings are the same. So if you think back a number of slides, I showed you that all those diaphragms had the same number. That one was drilled in line assembly, meaning those diaphragms could be swapped. They don't have a very unique position on the bridge. Then we have full assembly, and this is where all of your holes are going to be subject to a standard size, not just the field splice. So this includes the diaphragms. What does that mean? That means the contractor has to set up the bridge before they start their hole forming operation. And so you can see this bridge is both curved and super elevated. So the contractor needed to block it in its super elevated position, because now they're going to take every one of these diaphragms and they're going to put them up on the steel and they're going to drill them from the blank. So diaphragms typically will not have the holes formed in them. The stiffeners already will. So they'll bring it together and they're going to drill them to fit in that exact configuration. Does that make sense? So these are generally a bit more challenging to erect because that piece has to be installed in that location. And here, fabricators got the opportunity to put blocking every 5 to 10 feet, right, to manipulate that shape. Think about this in the field. How often do you have a shoring tower every 5 feet? You don't, right? Usually it's, at best, it's 2 cranes and maybe a shoring tower. Sometimes it's just 1. They have to manipulate that in the air. So you can see where we start to have fit-up problems, or have the potential to have fit-up problems. That's why it's important for you folks to know, was this fabricated as a line or an assembly? Right? Line assemblies generally come together pretty easily with not a lot of effort. Here's just another photo, that whole forming operation, getting those diaphragms installed. So, our example plan. Jump into your structural steel notes. How is that one fabricated? Line assembly. So count the notes. What number is that from the top now? Third one down. Because it's line assembly, what size holes will the diaphragms have? 3/16 are the oversized. And that is not in your plans. That's going to be in the specs, right? Okay. Match marking, I talked a bit about this. You can see you have your splice plate on one side, you have the girder web on the other, and these match. Right? This 67 is just unique to this particular plate. But this is what I was talking about with my example of how they sent the wrong plate out. And how does that happen? So when girders get painted, they have to be shot blasted before the prime coat gets put on. And so oftentimes you have 2 separate operations in this. Generally, these splice plates are smaller elements and can be taken somewhere else in the shop and blasted, where the girders are going to be blasted through a much larger system that takes up more space and more time. So to be efficient, they're going to move things all over the shop. So here you can see this is a girder going through a shot blasting operation. And because they get separated for a moment, if the folks working in the plant aren't paying attention, that's how that stuff can get mixed up. So you got a dirty girder full of cutting grease, probably some mill scale, things like that, going through the shot blasting, and it's going to come out with that nice dull sheen, fairly clean. At a minimum, we're coating our beam ends where there's going to be an expansion joint, so you can see we put that coat of primer on in the shop. This would be just the beam ends themselves, but if it's going to get a full treatment of paint, the entire girder would be shop prime. We don't do in Minnesota the intermediate or the final coat in the shops, partially because we're doing most of our painting for aesthetic purposes, and it gets so badly damaged by all of the other things that have to happen, right? The deck forming, placing the concrete, removing all of the forming, that it's just not worth it. States out east have had really good luck doing the 3 coats in the shop. So just a little bit of difference in our practices here. Okay. So once all of these things have taken place, and coatings are part of the fabrication process, just to keep that in mind. This material is going to be inspected by shop inspectors. So if it's a MnDOT project, it's our structural metals staff. If it's a local project, it may be MnDOT structural metals, it may be a third-party delegate that's going to be hired by that owner. And they're not just inspecting it at the end, they're looking at it during all kinds of different steps. So initially, when the plates come in, they're looking for material defects, they're reviewing all of the certifications that have to come with it, the mill certs, the testing. they're looking at the weld procedures that are being proposed before any of the fabrication starts to make sure they meet the intended specifications. They're reviewing the quality processes that are supposed to be in place, and then they're also understanding what the paint or coating system is going to be. So they're checking things along the way, but they're doing a lot of pre-work as well. Now, they don't just inspect the girders. Right? All of these elements are fabricated metal elements. And oftentimes they're out reviewing a lot of these. Because we don't do a ton of steel girders, our folks spend a fair bit of time inspecting ornamental metal railings and bearings. Because those go on any type of bridge. Can go on any type of bridge. Every product before it leaves the fabrication facility is going to be tagged with a shipping tag. And so this is more or less that final step that our shop inspectors are saying, yep, we've gone through the entire process. These are ready to be shipped. They're an acceptable material. So when these arrive on site, you gotta make sure that that tag is present. If it's not, you gotta start asking a lot of questions. And we've had this come up where they just ship a batch of railing without ever having it looked at. The last experience I had with that entire shipment had to go back and be recoated because they damaged it so badly on the trip from the fabricator to the construction site, we lost 50% of the coating. Never would have left the shop had our inspectors looked at it and said, no, you haven't protected this against all the damage that's going to occur. That kind of stuff happens, so it's important to see that these tags are present. You don't have to retain them though for our auditing and record keeping purposes because you're going to get what's called an inspection confirmation report. And so after our shop inspectors have tagged these things, they're going to compile these reports just to show that certain activities have been completed. It's partially for the prime to be able to pay his sub as well, that MnDOT has finally accepted all of this. And so these are going to be broken down by pay item. You're going to get it for all structural metal products. And this is what you need to retain for your paperwork for your audit. So this would be for a particular element. This is that modular expansion joint. Very, very simple, right? You're going to have a date to your project engineer. We inspected the modular joints. This was the quantity that was inspected where, and this is the date that should be on your final tag. If you have lots of different shipments, there might be a couple different dates. So you'll get this with each individual element. But then once all structural metals for a job have been fabricated, you'll get this final one that's going to list out every item that's been inspected, the quantities, where, and what the final tag date. So again, these couple documents are what you need to retain. Any questions? Alright, we're going to just roll into this a little bit and I'll give you a break. So I've spent a lot of this first hour talking about, I'll say, the very fundamentals of steel bridges, their elements to try to get you acclimated. We did spend some time talking about inspection duties that you're likely not going to be tasked with. But I do think it's important that you understand what's happening before any of these products show up on your job site, right? Because that little bit of background makes you just dangerous enough to ask questions when something seems wrong, right? And that's where folks like myself or Paul come in, right? Those are the calls that we really appreciate getting because it's way easier to deal with this stuff on the ground than it is once it's in the air. So because of that, there is still going to be some overlap between what our fabrication inspectors are doing and what you're doing, right? So we're going to receive the shipment. So this is one of the tough girders from Lafayette Bridge, Highway 52 in St. Paul. That piece, I think, is about 170 feet long. So that came from, I think, Gary, Indiana, fabricated those. So that came through Chicago, all the way through Wisconsin, to our site in St. Paul. So there's a lot of stuff that can happen in that transit distance, right? Right, it's sitting on an open truck. So when they arrive, you need to make sure that that inspection letter and the tags are present, right? And before they pick it off the truck, you want to do a thorough visual inspection, right? Now I recognize that can be challenging. You can see the cab of this truck, right? It's going to be pretty hard to do a thorough inspection of the top plate, right? So do the best we can, especially if you're trying to work with traffic closures and we want to stay safe. But it's a relatively straightforward, simple task. to walk along the bottom here, make sure there's not significant damage to coatings that can't be repaired. We've had these come out before where this back end, that whole bottom flange was bent, right? That's gonna be a challenge for the contractor to make up their splice in the air anyway. So we want to address those things on the ground. So we want to understand that. And I will tell you that if there's damage that is very challenging to repair in the field, if you let them unload it because they say we'll come back and get it later, they'll never come back and get it later. Okay? I dealt with a bridge up in Baudette where the beam, the driver, I think what happened is probably fell asleep and his little trolley ended up in the ditch and he drugged the girder for about 200 feet before he stopped. Wrecker was able to get it all up, they got it to the job site, we wouldn't let them unload it from the truck until we were confident that the beam wasn't damaged. Right? That beam came from Wausau, Wisconsin, but that also not a very short drive. Right? But we were able to work through it.
They said that they all went back to Wisconsin and did more.
That one, no, we did inspection on it, we found out that it probably ruined the pavement way more than any damage on it. But it took about a day, because we had to get people up there to do some MPE. We had to take a bunch of thickness measurements. Had some pretty good road rash on it. It was a blacktop pavement, and it still thinned up the section by about a 16th for how far it drove. So, contractor was really good on that one. I mean, they worked with us. They were in a bit of a schedule crunch because it was late season, but they understood that it was to their benefit to not send it back, right? So make sure you're having those good open conversations about it. So like I said, we're gonna do a visual inspection, again, looking for bends, nicks, scrapes. Coating damage is fairly common, right? It's trying to assess the severity of it. Is this something that we can deal with later on in the field, or is this something that we have to deal with now or potentially send back to the shop? Elongated bolt holes, if they don't snug up, if they bolt things together for shipping, generally they're not filling every hole, and things can wobble around and ruin some of those holes. So making an assessment of, was a lot of them damaged, was it just one? We can make some of those judgment calls or call somebody like myself to help you out. Everything they said they were going to ship, is it here? Is it in the ditch somewhere between here and there? Sweeping, warped elements, this happens occasionally, something to look for. It's hard to deal with in the sky again. And then once you got through all of these things, you gotta watch out for the mishandling in the unloading process. I will say that last bullet is far more likely to occur on ornamental railing, partially because they're smaller elements, they're typically picking them with a forklift. Oftentimes you see damage to the coating if they're not careful. And that's something we want to get on top of because it's not easy to repair. We've gone almost exclusively to powder coating, and that is not an easy thing to fix in the field. So again, I want to emphasize, if you see damage that makes you uncomfortable, do not let them until you've got comfort in doing so. The elements need to be straightened. We do permit some level of heat straightening. The spec book has some of these general limitations in here, but the biggest piece I want you to take away from is they gotta have a written procedure that every party is gonna agree to. Heat straightening is much more of an art than it is science. It takes very experienced people to do it right, not Bubba the iron worker with his little fire iron. And so it needs to be well thought through before we go through any of this, particularly if it's an element like a beam that's going to be carrying a significant. And it's something that we can work through. Just got to get the right. So you've gone through all these checks, everything looks good. Typically, the contractors like to have the trucks come and then place it right onto the structure itself. But if you do have to stockpile it, store it on site, just make sure it's in a well-drained area, you don't have vegetation all over. We always want them up on skids because you never really know if they're going to ultimately sit in a pile of water. I was on a job in Grand Forks. Red River was starting to flood, and the contractor took them 2 days to move all of their rebar out of where it was going to flood. Right? So it's important to kind of think ahead a little bit, especially when you can understand the schedule. And then girders do need to be stored upright. So you can see that can present a challenge. This contractor provided some these angles to provide stability because we want to keep a safe environment too, right? Your fasteners themselves, we've had such a problem with contractors not treating these fasteners appropriately that now we require a fastener storage plan. This is a submittal that they have to go through to show us, or to commit to us that they're gonna actually take care of these things. It's simply, we should say, most generally I see Connex boxes with all bulk kegs put in there at the end of each ship. So it's not like this is a super onerous thing. But I've been on projects where these bulk kegs, they're opened up, the iron workers will generally stuff bolts so that it's easier to work with up in the sky. I've been on job sites where they've just left them open, and then they go home for 3 days because of rain delay, and they come back and punch holes in the bottom of these punch holes. So can you about imagine what the condition of what those fasteners were? Yeah, so and unfortunately we've had to put provisions in the specs to address this. And this has solved, I'll say, about 90% of the problem. All right, 9 o'clock. Let's take about a 5 or so minute break. Certainly, if you have any questions during the break, feel free to come up. Is that loud enough back here?
Yeah.
This on the
Right.
pause.
So before the girder has even arrived on site, and so this next bit, I know I've been talking a lot about steel in general. For the next 2 hours, we're going to really talk about the erection process of the beams of the girders themselves. Not so much about some of these other steel elements like the ring. But before any of this shows up on site, you've done a lot of work on your substructures. And we're going to talk a little bit about the bearing seats themselves. Because if you think back to the hole forming process, we have 2 sizes of holes, right? What were they? 3/16 and 1/16, or an oversized or a standard hole, right? Now, your ability to fit that up is going to depend a lot on how close to the tolerance your bearing seats are cast, right? If you only have a 1/16 of an inch slop, and let's say your bearing seat is an inch low, is that going to work? Not well. Right, so we do spend some emphasis here on these bearing seat tolerances, because I've gotten burned on a project big time on this. So it's important to know the assembly type, because the assembly type is tied to the tolerance. So let's go through the criteria. So even though there's a write-up in 2402, it essentially sends you back to 2401, where we walk through placing these bearing seats. So prior to casting, form's got to be set within 1/100 of a foot, which I recognize is a bit of a challenge to consistently do with the surveying equipment we typically have. That's what the spec talks about. We do specifically tell the contractors you can overpour and grind. We stay silent on the ability to shim because it's not desirable. So we specifically call out this. Anchor rod's got to be located with the template, right? So if you think about a pier cap, we might have a number 11 bar. We probably made it a number 11 in design for a reason, right? We want all of that steel there, not to have the core right through the rebar. So it's important to do the template for your anchor rods. And if you have anchor rod blockouts, or those ground tubes that I talked about a little bit earlier, they have to be appropriately placed. And now we have a requirement that they got to be checked with surface. So that's all prior to casting, prior to placement. After you've cured all this, we've got a couple different things they got to look at. First, it's got to be a level surface, right? We've had to go to the extent of defining what level is. Generally, for most of our structures, because we're doing precast beams, you're going to just have an elastomeric pad there. It's a steel base plate, which you may see with a lot of these longer span steel structures. You've got this basically 6 inch over the width of it. pretty tight tolerance for level. We do ask that the center line of bearing be surveyed for elevation and XY coordinates. This is an extra step because if the contractor did a good job, most of this data, especially the coordinates, will get thrown out. What I will tell you is it's really hard to collect this once the bearings are in place. So that's why we ask for it as a hold point. As an inspector, you're going to work with the contractor to look at the elevations because that's where another tolerance is going to kick in that we'll talk about. So we take that elevation data, we're looking for two things. They have a tolerance for the plan elevations, and then they have a tolerance for what's called the differential between adjacent seats. Right? So let's think about that for just a moment. If every one of your bearing seats is set 1 inch low, that's scenario one, compared to every one of your bearing seats is set at the exact spot except for one. One is set an inch high. Which do you think is going to be a bigger problem? The second one, the differential. Why? Throws a lot of things out of whack. Yeah. If everything's low, right, we fabricated a system in a certain plane. And that system doesn't care if it's 100 feet in the air or 6 inches off the ground. It cares about the plane, right? And so as long as all of your seats are where they're supposed to be relative to one another, the only thing that cares is the roadway geometrics, right? Now, if you think about having everything is supposed to be set like this, but then you have one bump. Did your system get fabricated with that one bump in mind? No, so I've seen a job, it was a steel bridge where we had really stiff diaphragms. And we had something like that, where you had one seat that was sticking up a little bit higher. Those diaphragms were so rigid that it picked up not only the next two beams, but then even farther away. So one girder was holding 4 other beams up. Right? Those diaphragms were not designed to do that. That was okay because steel deadweight by itself isn't a lot, but then you put a concrete deck on it, and then you put traffic on it. It would have broke those girders, or excuse me, it would have broke those diaphragms, right? So that's why these beam seat tolerances are important, and they ultimately do feed into how well everything bolts up together once you're up in the sky. So let's walk through them. Differential. So we put this equation in the plan, but basically what you're going to do is you're going to take your plan elevation minus what you surveyed for one bearing, or excuse me, one beam seat. Go to the next one over, and you're going to do the same thing. Once you have those two numbers, and we'll walk through this, you're going to find the difference between those two. So if it was all poured exactly correctly, this should be 0, right? Because everything matches up. 0, 0, 0, 0, right? We'll walk through an example. This tolerance is going to depend on the fabrication method. So if you have full assembly, this differential can be no more than 1/8 of an inch. If you have line assembly, remember oversized holes, or pre-stressed girders, because they have oversized holes in their diaphragms, you get 3/8 of an inch. So not a ton of tolerance here, but certainly there is a difference, right? Plan deviation, we allow no more than 3/4 low and no more than 3/8 high. I'll suggest that these are hard things to survey, right? So just kind of keep that in mind when you're working with your contractor. And then if they do find through either one of these checks that adjustments need to be made, it's got to be accepted by the engineer. Right? Because we don't like shimming. The contractor is going to propose to just shim everything up and walk away. That becomes a maintenance issue long term. So generally, we try to work with them to do a combination of shimming and grinding. So let's walk through this in your manual. If you want to walk along, in the back of this, I think there's some blank space to do this. Otherwise, just feel free to follow along. So we're going to do a hypothetical problem. You've got your beam A and beam B. This is what it looks like in the plan. plan gives us these elevations. Contractor goes out, does his survey, everything's pretty good. For whatever reason, the concrete's settled. Maybe it's on a spread footing, so the whole substructure itself may be settled a little bit, and we end up with differences. So A came out lower than planned, B came out a little bit higher. You can see that difference. So what's the numeric difference? A is about 5/8 low, B is a quarter high. Doesn't seem that bad, right, when you think about concrete in general. I mean, that seems pretty good, right? But now we're gonna put a steel structure on top of it that's gotta fit. So, let's do our basic check. We're 5/8 low. Does anybody remember? Is that too low? Nice and loud for me. 5/8 low. That's okay, it's 3/4. So we're okay. So both of these were okay. Our planned deviation were okay so far. Now we gotta go into that differential. So you've already done the math to see how far off of plan they are. And now we need to check the difference between these two differences. Okay, so you're gonna take the negative 0.5 minus the 0.2. Come on. 0.07. So that's going to be a little less than an inch. Does that seem like that fits any of the tolerances we talked about? So go to our plan sheet, find that it's line assembly, so we get 3/8 in this case. No, we don't need either of them, right? 3/8. So the contractor's got to come out here with a plan. Now the tricky part about this, generally we don't have two girder systems, right? There might be 7. So we've checked A and B. Now you need to check B and C, C and D, E and F, right? So you may think, well, yeah, it's really easy. Let's just grind this one to get us closer. Well, grinding this one might put B and C out of tolerance. That makes sense, right? So it's important to approach this as a plan. Right? That's why we emphasize that the engineer needs to accept this, is we don't want them to necessarily push something else out of tolerance. Okay. Does that make sense to everyone? I mean, you're going to do this on pre-stressed beams too, so this is applicable across the board. So you've got your beam seats all settled, they're in the right elevation or meet the tolerances now. You've got to prepare to get the beams up in the air. So if you have a bearing system, sometimes they come wrapped up with protective coatings, things like that. If those aren't intended to be incorporated into the final structure, you're going to remove that kind of stuff. If there's areas that need painting because they're going to get covered up, you're going to take care of that. You're going to set your bearings in place. 90+% of the time, if it's a fixed bearing, you're not going to put the anchorages in, but again, that's something you're going to have to look at with your installation instructions. And just be prepared for those beams to be in place. Set those bearings, make sure you understand where they are. Now, oftentimes, contractor is going to be in a site where they can use shoring towers or false work. We really strongly encourage, we won't require often, but encourage the use of false work because they can help support the girders when they're not on the crane. They assist with stability, which can be a safety thing, and they control the deflections or that cambered shape, right? Unique thing I didn't talk about. So in Minnesota, almost always the girders are fabricated in a no-load condition, meaning gravity is not on. It's very easy for the fabricator then, because they can block it. I mean, they can do their best to turn gravity off. It's a little more challenging for the contractor, right? Because can we block something that's 100 feet in the air and take gravity off? No. So that's an important difference because contractor has to understand that they're going to have to do some manipulation with however they're picking these things to make your splices fit. So that's where this false work can be very advantageous. You can just place it in appropriate spots. So false work is going to be used. And there are some situations where it's required, but if it's gonna be used by the contractor 42 days prior to its installation, they have to submit plans and calcs. These have to be certified by the contractor's engineer. We do require a professional engineer to develop these. As an inspector, you don't need to thoroughly review these plans, right? This is a contractor's document. But we do want you to have very good familiarity of them so that when you're walking around on site and something doesn't look quite right, you can say something. Because we've had this issue before, and I think I got a photo coming up here, so I won't spoil it. So basic understanding of what they're planning to do is very important as an inspector. So what do these kind of look like? They're all going to have stage-specific notes. In this phase, we're going to have these 3 or 6 towers. Our crane's going to be located here. This much of the system is going to be erected. Because sometimes the contractor will hopscotch these around. So you're going to have those stage-specific notes. You're going to have elevations. This is really important. Again, not for you to check, but to see that somebody has done the work, right? Because we had an instance where the contractor came out and they had the elevations. I think they were correct. Nobody ever checked that it was installed to those elevations, and it was 6 inches low. So that when they went to land the girder was stiff enough that it never landed, right? It just held itself up. Pretty hard to go on to the next phase of your erection sequence when you're depending on the girder being supported like that. So the contractor had to stop, figure out how to shim everything up 6 inches, right? Again, that's their onus, but be aware of it, right? The shoring tower is probably one of the bigger things that you want to be aware of, because I have seen this happen, is they'll call out, typically it's a commercially available shoring tower that has a capacity. Sometimes they'll even tell you it's going to be red, it's going to be yellow. Those are the things you want to watch for. Do they meet the specification? Because if it's something different, maybe it's supposed to be a 100-ton shoring tower, but they brought out a 50-ton. Does that sound like that could be a problem? Yeah, right? Are they in the correct locations? An engineer has designed this thing to handle the stresses in the girder, but if they decide, you know what, we're going to put it 50 feet back because that's more convenient, do you think that the girder is going to behave the same? Probably not, right? Elevation's been verified, again, that's on the contractor. Did they modify it? Did they cut a leg off the shoring tower? Does that seem like a good idea? It hasn't been like that? Right. Are there any buried utilities? We almost crushed a 72-inch pipe because contractor didn't locate the utilities ahead of it. That would probably have been bad, not only for the utility, but the steel would have dropped too, right? So again, we require a whole point that they do that survey and location. And now we've gotten to the point, because we've had a few issues with this, that the professional engineer that certified the plans has to provide a written inspection letter. Sometimes we will back down a little bit on this and allow a competent supervisor to do this role too. But that's the communication piece that we're going to talk about in front. And so you can see this can be really important, right? So the photo on the left, this is pretty typical. You'll see, a lot of times they'll just plant 2 shoring towers. You can't see the other one because it'll be over here, and then they'll have a spreader beam. So you can see here's a temporary bearing for that next beam to come in. Common in a lighter system, right? This is your example bridge. These piers are 180 feet tall. These are significant shoring towers, right? That are carrying a lot of load, not only vertically, but this canyon had a lot of wind coming through it too. So they have to be stable against that wind, especially once you get these big sails up here that are going to collect that wind and want to put it back down in here. So it's important to have that basic understanding, and if you see something that looks wrong, say something. And I don't see the photo coming up here, but I know it was roughly 10 years ago, there was a shoring tower system down in Illinois, and I believe what ended up happening is the contractor brought out the wrong capacity shoring. Called for 100 ton, they brought out an 80 ton, something like that. Very light breeze outside of the work shifts. Unfortunately, nobody was on the site at the time. Caused the whole system to fall off and end up on the ground. Right? It's catastrophic to your project. Obviously, get a big chunk of steel landed on somebody, it's going to be catastrophic for them, right? So that's where I really emphasize the safety piece of this. You don't have to be an expert in this, but if it says there's supposed to be a 100-ton shoring tower out there, it's probably a good thing to just go verify that before they hang the steel. Does that make sense?
Susan?
Yeah.
How do you do that? Do you like just talk to the contractor or how do you?
Yeah, so it's a really good question. The question is, how do you verify that? So a lot of times these things will have stamps on them. You know, it'll be like a Safeway T200, right? It'll be stamped right on the tower, especially if it's a newer one that hasn't been beaten up. And so you can go to your erection plans and see that, yep, that's what's here, it matches. Sometimes you won't have those labels, and that's where you gotta start talking to your supervisor that's out there, right? Talk to the contractor and have them prove to you, right? Especially if you're suspecting something's wrong. Another example I'll give, so I got a call once a couple of years ago, hey, we were placing the deck and the overhang brackets just failed. Our paving machine is sitting on the wet concrete, we need you to come up here. So I drove up, it was up by Osakas. And first thing I noticed when I got there is in the area that the paving, or that the overhang brackets had failed, those brackets were a different color than all of the rest of them, right? That was pretty obvious. So I asked the foreman, what's going on here? Oh, we ran out of paving, or we ran out of these brackets, and we're building another bridge 5 miles south here, so I just went and picked up the last 10 I needed from there. So I went up and looked at them, and it was very evident that the rods that support that diagonal, one was, we'll just say one was a ½ inch, the other one was an inch. It was that obvious that the member sizes were different, right? And then on top of it, one was red, one was blue. Like, so it never should have happened, right? But nobody said anything, right? Fortunately, this was over the slope paving, not over 94, right? Because that would have been worse. Nobody got hurt. We stopped the war, we got it just fixed. But that's the kind of stuff that can happen, and it seems really simple, right? So just ask those questions. That's a really good question. Hey, how do I know this matches your plan? Prove it to me. Avoid those mistakes. We also require erection plans. And so this is that detailed sequence of how the contractor is going to install. So like with our plan, you see the bridge in its completed state, right? The framing plan shows everything linked together. But that's not how we build these things. They come together in pieces. And we have to maintain stability and strength throughout the whole thing. And really, so the purpose of this is to show that the contractor has thought through that sequence, they understand how their girders are going to be delivered when, and that they're demonstrating stability throughout the entire process. We don't want to damage these girders before they get all of their loads on them, right? And they're not necessarily, the engineer of record typically is not designing for an erection sequence, right? Because we don't know how the contractor is going to do it. We don't dictate their means and methods. So they need to demonstrate to us that they're not going to damage the beams based on the sequence that they want to do. So erection plans are going to be required if there's any sort of public access allowed under the bridge when it's not in its completed state, because we haven't analyzed that yet. So think about, let's say you're building something over I-94, right? And you only have a 12-hour closure period, so you're going to get so much of the work done, then you have to open it back up to traffic until you can work again the next night. That would be an example of when you have to have an erection plan. Sometimes we'll put it in the special provisions, so like that Highway 53 bridge in your example plan, that was over an old mine pit, right? There's nobody underneath there other than the contractor. We still required it because they were such long spans, and we wanted to make sure that stability could be demonstrated. These are going to be reviewed by somebody like myself. Again, we're expecting you folks to do that same thorough review to understand the sequence, right? Especially when it comes to tightening bolts, which we're going to spend a lot of time about in the third hour. Any deviations from that plan, they have to be approved by the contractor's engineer. So that's the person that was in charge of developing that, not the project. Things to look for. You have the necessary traffic control. If there's a shoring tower that's supposed to be set up on the shoulder, is there adequate barrier to protect that? Is there sufficient space for the cranes? We had a contractor submit one of these once where the crane was going to be located on the 2-to-1 slope paving. I haven't seen too many cranes operate real well when they're sitting like this, right? So those are the things you want to watch for ahead of time, right? Does the sequence match what's available on site or the delivery schedule? Do they have the match marks in there? Does it make sense what they're asking for? Are you referencing those match marks? The rigging devices or lifting devices that are shown on the plan, is that what they actually have or what they're going to be bringing? Because those things have capacities too. Crane capacities they match what's available on site. Correct number of bolts and pins, we're gonna dive way into this. Are they proposing that correctly? And are they looking at the diaphragm installation correctly? There's also a lot of max wind speeds that the cranes can operate at. Are they planning for that? Are you monitoring that? So what do these look like? You know, again, you're gonna have that general site plan. You're gonna see how the girders are gonna travel into the site. Here they're telling them that they have to back in. This is over railroad tracks, so they're noting certain utilities and certain setback areas that they need to watch out for. You're gonna have some general notes that apply to all sheets. This is where you're gonna find that lifting device rigging information. This is probably where you're gonna find your wind speed limitations, things like that. And then you're gonna get into these sequence notes, these stage-specific notes. And so this one in particular, you're placing your crane here. This one says that we're gonna bring in the towers and then hold piece number 121G 104 with the crane while we brace it against this other element. Right, so it's going to be very specific because again, we're trying to demonstrate stability, keep a safe environment. So they've got through all this work for the day. At the end of the day, we have to make sure that if there's tie downs necessary so that the bearings don't lift up, that they're in place. There's also accommodations to keep these girders from rolling over because an I shape is not very stiff in its horizontal direction, just in its vertical. And we do require that you have side-by-side girders with the appropriate number of diaphragms installed for stability. Because again, if you see something, say something. So I did get ahead of myself. This is that Illinois reference. This was, I think this was under like a 5 or 10 mile. So nothing significant, right?
Nothing underneath it.
No, I don't believe there's any fatalities on this. Unfortunately, it's not over that roadway that's way back there. Yeah. Everybody should get to go home every day. So let's kind of go through a brief tour, just to wrap your heads around what this might look like. So girders, you've done all your pre-planning, right? Your bearing seats are in the right spot. You've got your bearings set. Your erection plan has been approved. Shoring towers are installed. They all look good. Girders coming to the site. So you're bringing in a haul road. You can see here, the contractors starting to stuff their bolts in one side of the splice. This is a lot of effort. Can be a lot of work to do out of a basket. Oftentimes you can see that their safety lines are installed. This is a time too, if you're savvy about painting the spots for your construction elevations, you can do this while it's on the truck or on the ground, as long as provided it's safe. So they're going to prep all this on the ground. They're going to get ready for the pick. You can see these are rather large lifting hooks, lifting devices. These are going to be in that erection plan. There's going to be a location for these. They can't just willy-nilly put them anywhere. It's something to kind of keep an eye on, right? Do you have to physically go up there and measure it? No, but it'd be nice to see if the iron worker's got a tape measure out or it's painted a spot on the beam or something like that, right? Watch that. Look at the match markings while it's on the ground. Is this the piece that we thought it was going to be, right? Especially if trucks are coming out over it. So now you're going to pick it, pulling it up in the sky. Here you can see that they joined a bunch of the diaphragms together so that they can pick this with I guess this is 2 cranes here, but that keeps it a lot more stable, especially with that curvature to it. It really wants to flop around like a wet noodle when it's curved like that. So you're going to lift it into place, and then they're going to typically, if they're bringing it into a splice, they're going to drop it in from the top down so that they can just mate up with that bottom plate and use gravity to their advantage. Are they following their direction? So you can see here they bring it in from the top down. They've probably got this far end picked up just a little bit so they can slide it in because they've already have their sandwich somewhat made here. So you're going to have your field splice plates are going to be both on the top of the flange and the bottom of the flange, each flange, right? You can see how it's going to sandwich together. So they're going to kind of finesse that into place. Again, here they pre-stuffed a lot of these holes. This particular splice, this is the GIB 52 in St. Paul. This one I think has 600 bolts in it. So not a small effort to go through it and tighten all that. We do require, and this one, very much so lacking on this side, we do require pins. So this is a drift pin. We'll talk a lot more about these drift pins. You can see it has a tapered end on both sides and then a full barrel. That full barrel is to match the hole size, not the bolt size. So if we have a 7/8 inch bolt, that barrel is gonna have that plus 16 bit. That makes sense? Why do we do that? The pins are used to ensure geometric control. We're gonna dive way into that coming here. Get your field splices installed with the appropriate number of bolts and pins. We're gonna go in and feed the appropriate number of diaphragms. Within their erection plan, it should tell you how many diaphragms they need to install before they have hooked the crane. Okay, this will vary. It's not always all of them. Typically, it's not all of them. So they'll come in with a smaller crane and feed so that they can keep going with the larger crane. So here you can see they've got these two, they don't have any of these yet, so they still have the crane hooked up because they're not to a stable point. We're going to do some permanent bolting, which we're going to dive into, but the big takeaway right away is we're looking for uniform snug tightening and tensioning. So bolting is a multi-phase process. It's not just stuff to bolt and tighten. Got everything bolted in place, all of their final bolting has occurred. They're gonna make sure that any remaining safety lines are installed. You get your stool elevations, you're gonna start your decking. Once the decking's in place, we're gonna install those shear studs. The inspector, you're gonna observe that installation. Place the rebar, place the concrete. So assembly, we have rules around assembly, primarily related to when things can be tightened. So the spec book defines a primary member as any member that's going to carry primary stress. This is a pet peeve of mine, right? When you use the same word in the definition. So what is a primary stress? That is going to, I like to think of it as, is this a member that's going to carry live load and contributes to the stability of that. So the spec book breaks it down that beams and girders are always primary members. That makes sense, right? They're carrying any of the loads back to the substructures. The diaphragms and cross frames can be considered primary members, but they're not always. And so we've simplified it by simply stating that if it's fabricated in full assembly, those two are going to be primary members. When you have a primary member, it requires a pinning and bolting sequence to be supported. That's the big difference. So in our plan, what was the assembly type? Line. So the only spot you need a pinning and bolting sequence is for what element, or what part of the girder? What was that? I'm sorry? Yep, the girders and beams, but what part of the pinning and bolting? There's only one element on that, because there's lots of things that get bolted together. What's the element that needs to have this? The field splices. Yep. The diaphragms are not required to have this because they're going to have oversized holes. Does that make sense? Pins. Passing that pin around right now. Pins are necessary to maintain geometric control in the drilled condition because they're the same diameter as the hole. We also have erection and installation bolts that are going to draw this together. So you can see this is an undersized pin. Contractor's already got a bunch of bolts in. And if you look really closely, you kind of see a little half moon in there, right? Pins help prevent that. And even though we think of steel as being very rigid, when you get to some of these heights, like 7 feet tall, 15 feet tall, and this is only a half-inch thick plate, it's really flexible. Right? And so that I'll show you a picture here in a little bit. I've seen some of these splices where they have up to 600 bolts in them, that if they work these connections wrong, you can fill up a quarter of the hole with these half moons. It doesn't seem possible, but it is. So pins are really important. And generally, your ironworkers don't want to install pins because then they have to take them out, right? So it's more work. But I will suggest that upfront work is really necessary to prevent a lot of downstream problems. So our spec book, in the absence of any engineering, requires that 25% of the holes be filled with pins, 25% of the holes be filled with bolts that are snug tight. The rest can remain open. They need to be well distributed. Right? It doesn't do us a whole lot of good to put 4 pins right in the middle and expect that the holes out in the corners are going to be in the right spot. So you can see here, I apologize if you're colorblind, I've got red representing the pins up in the corners. Because right, it's hard to rotate something when you're pinned way out on its ends. I've got a couple sprinkled in the middle, and then I've got some snug tight bolts more in the middle of the connection because we're trying to bring all those plies together in this most part. Keep in mind this 25%, we're not looking at the connection as a whole, we're looking at the individual elements. So you have to look at 25% on the top flange on this side of it, 25 on this side, same with the web, 25% here, 25% here. They can't just put all of their pins in the top flange and then bolts everywhere else. Does that make sense? It's well distributed throughout the entire connection. Here's those misaligned holes, kind of a blurry picture. So this is after, I think about 40% of the bolts were put in. So you would think this should just be a 1/16 of an inch slot, right? There's that much flexibility in this place that we got that far off. So they had to take all the bolts off. That's extra work, extra time, right? So erection pins, drift pins, again, I've kind of harped on this, essential for geometric control. They are strong enough where they can do some load transfer, right? We're bearing right on them, so they have to be. Sometimes that's why the contractor may ask for more of them, right? Because there's enough of a load based on their sequence that they would overstress, the pins. They do have a little bit of a tolerance, right? They come out of the shop +0. They're allowed to be a little bit undersized, right? Because they are a machined element. What's important for you to realize, and I like to walk around the site and look at this before the operation starts. Take a look at these pins. I mean, they want to use them forever and ever, right? But eventually they start to turn into a little bit of a dog. Once they get like that, they're probably not going to work as well before it's time to toss them. Spec book defines 3 types of bolts: permanent, erection, and installation. So let's walk through these really quick. Permanent bolts are used in the final configuration. These are to maintain geometry and strength throughout the rest of the life of the bridge. We do allow these permanent bolts to be used as erection bolts, provided they meet these conditions. They haven't been tensioned up yet, so they haven't been fully tensioned. They still meet the as manufactured condition. They're not elongated, which you test by running the nut all the way up the shank and back. So even though you only need to do this if you suspect damage. So if we look at a bolting assembly, which I'll pass along earlier, or in a little bit, typically in the final bolted condition, you'll have less than a thread of stick out. Maybe it'll be flush. To test these things, to make sure they haven't elongated, you have to go all the way through the run of threads. Because we don't know where it might have elongated. So if you suspect that, you got to take the bolt out, you got to run it all the way down. It's the only way to do it. Contractors, I would say 90% of the time are using the permanent bolts as erection bolts. And so we'll get into that. So let's talk about bolt installation because this gets to be important. Remember the DTI? We always want the DTI opposite of the turned element. When we install bolts, primarily, functionality in a sense. When you have fascia girders, we want the heads facing outward. Looks nicer. And that's on your webs, because you have that. Their bolts are going to be oriented horizontally. When you install bolts in the flanges, we want the heads facing down. And that's primarily because if some of these bolts are not tensioned properly, they can vibrate themselves loose. Very, very rare. Now it seems counterintuitive, right? That, because then you're going to drop a much larger bolt instead of just a nut. They don't loosen themselves up overnight. By the time the next safety inspection comes, you're going to hear these things rattling around. You'll have time to recover. So that's partially why we do it this way. Configuration is important, so as I alluded to, the DTI's got to be opposite the turn element. You're going to place that hardened washer on the back side. This is the required configuration unless they demonstrate that it's not possible to install the bolt this way. And I would venture to guess 95% of the time you can accomplish this. Iron workers don't like doing it this way. Does anybody know why?
Work from underneath.
What's that?
Then they have to work from underneath.
That's part of it. That's definitely part of it. Think about the scenario where you have a 15-foot tall web. You're doing the bolt that's right in the middle. I know we don't know a lot about the DTIs yet, but we have provisions where we are not allowed to fully crush them. So if you have a 15-foot tall web, can you see your DTI?
Someone's gonna hold it up, right?
Yeah, you have to have two people, right? And you have to somehow communicate back and forth while you're rattling up bolts, right? Especially if you're using air guns, it's a noisy operation. So you'll get some pushback. I mean, it's probably gotten better now because we've clarified this in the spec, because it becomes a two-person operation. This is the required operation unless they demonstrate it's not possible. If it's not possible, we do allow the DTI to be on the turn side, but they have to insert a hardened washer between the nut and the DTI. This is primarily out of concern that if they let it rattle too much, you can grind down the protrusions. Pretty low probability of it happening, but it could happen. And then the final configuration would be to allow them to turn the bolt head. If for some reason there's maybe a stiffener is at an angle and that's the only way we can access it, that would be the other opportunity to reconfigure this. We're going to talk about why it's important to have the DTI opposite of the turn element in just a little bit, so just want to plant that seed. If you have an oversized hole, this is where that extra hardened washer comes into play. That extra hardened washer, no matter what the configuration is, has to go underneath the DTI. The DTI is soft enough as compared to the base metal that it's going to deform with that hole. And so we had the project that I was referring to where we had to go replace a lot of them. What ended up happening is they were installing their bolts, their DTIs all looked like they were crushed, right? The protrusions were flat. And we started looking at, well, no, that washer's missing, so we made them take a couple out. What had happened was, because this hole is slightly smaller than the hole of steel, the DTI sucked into the hole. None of the protrusions were crushed. So you can see the outline of this hole in the steel beam in this DTI. So we had no idea how tight it was. That was partially why. That hardened washer prevents that because it gives it a good strong back. Does that make sense? Again, something you want to check for before they start stuffing holes. Moving on to erection bolts. These are used to hold the members in that snug, tight condition while the pins are still present. They can be used as geometric control if they're fully tensioned. That could be in your erection plans. It's something to kind of be aware of. And these are going to be the same size as the permanent bolts. Because again, they generally are doing their permanent bolts as their erection bolts anyway. Installation bolts are used to just simply hold the pieces together, often for shipping, sometimes for setting things up in the air. They're not going to be incorporated into the permanent structure because we have no idea where they came from. There's no certs available for them. Oftentimes, if they're black bolts, they might not even be the right size. But we do allow them to use these to assist in their operation. So what's the general sequence for making up a field splice? You're going to install some of your installation bolts. Again, to just kind of hold things in their relative position, right? Because all this work gets done in the sky. Very minimal in general. Once you bring your pieces together and they look geometrically okay, you're going to install your series of pins. This is a spot where the contractor may tweak things a little bit up and down with their crane to try to bring everything into alignment. If they do a good job, especially if they have a good crane operator, those drip pins, they shouldn't have to have a huge maul out there hammering away to get them. You really should be able to slide through a simple handheld maul. They gotta be out there, especially if it's on the top plans. I've seen jobs where they come out there and they're swinging away like they're chopping wood to try to get that drip pin in. Something's not right. They really should, even though it's the same size, they really should, I'll say, slide in. This 25% can be substituted for bolts if there's a plan. You will never have a job though where you're not gonna have at least 4 drip pins on each one. Because the bolts can't set geometry. Right, they're undersized. Once you have the pins in, you're gonna install your erection bolts and snug tight them because we wanna start to bring all of the pieces of steel together into contact. If you have installation bolts in place, these don't count towards the 25%, so they might have to pull those out and substitute them. And this 25% is important because that's what dictates when they can let the crane off. They absolutely cannot let the crane off until they have 50% of the holes filled with something. If they need to fully tension the erection bolts, they would do that now at this phase, remove any remaining installation bolts that haven't been taken out. Then they can unhook the crane. So it should look something like this, well distributed. Here's another take on it. This is a ground splice, but the theory is still the same. Maybe a little bit hard to see here, but more or less what they've got going on is every other line is pins and every other line is bolts. So I would say this is well distributed, right? Probably overdid it on pins and honestly could have gotten a little less. That's fine. We're not gonna tell them. So now they're going through, checking the fit. In this case, it's pretty easy because it's on the ground, but this is where they're gonna take that look. You see any half moons? Does anything look warped, twisted, whatever it may be? We're going back and looking at the bearing assemblies. Is there any uplift? Do you see a gap? And sometimes there will be, and that's okay if it's been denoted in their erection. Because girders are gonna take on multiple shapes, which we're gonna talk about here a little bit. They may have to make adjustments to the members. There used to be some very hard tolerances specified in 2402. What I want you to take away from this is those tolerances really are intended for the final position, not these intermediate steps. And you don't want folks going out there trying to survey exactly where the tip of that cantilever might be, while the beams are still wanting to deflect in all different shapes. So that's been a little bit different change in practice. Once we're comfortable where everything is geometrically, we're gonna go through and install permanent bolts in the remaining holes. Field splices, unless the unless the contractor's erection plan specifies, field splices really should be tensioned up right away, right? Because we've already locked in that geometric in the as fabricated position. Let's just solidify that. So field splices really should get done as soon as you're comfortable with the fit up. Not let a whole bunch of other erection happen and then go back. Diaphragms are a different story that we're going to talk about. So they're going to install in the open holes the remaining permanent bolts, and they're going to start to systematically tighten these things. This is where that pinning and bolting sequence comes into play. They really should be working from the center out for tightening. Tighten all of these, come back, and then remove the pins. Again, unless they've told you otherwise in that plan, because they've looked at it. So we're going to talk about that systematic tightening in just a little bit. Again, my slides get a little all over, it looks like. So permanent bolting. I've talked a lot about this. Again, this is that bringing it into its final geometry and strength for the rest of its service life. A bolt is defined as fully tensioned, permanently bolted, once it meets this minimum tension requirement in the bolt. Now this is kind of an odd way to think about a bolt, right? Because I would assume most of you are familiar with tightening a bolt based on torque, right? Torque it to this amount. That's not how we do this for structural bolting. So we're bringing it up to a minimum tension, which is defined in the spec book. So for a 7/8 inch bolt, which is what we're typically gonna have, it's gonna be 39,000 pounds is the minimum that it has to be tensioned to. So why do we tension them? It prevents slip within the connection, right? You have slight oversize in a field splice. Diaphragms might have a little bit larger, right? These are designed, so usually we think about a bolt having steel bearing right against it, right? And that's what transfers the force. In a bridge, for serviceability and to give ourselves an additional factor of safety, we rely on the friction that happens between all of the plates. And in order for that friction to develop, the bolt has to tension it all into place. And that's a safety factor, right? Because if you were to experience an overload on a bridge, which happens, it first has to slip everything, and then the bolts go into bearing. And because it takes more bolts to develop that shear force, you have excess bearing capacity. So it's a safety thing, so that we can tolerate oversized loads should they be presented on the bridge. So it's a friction connection, not a bearing connection. We also want to make sure that through the tensioning process, all the bolts are carrying about the same load. So if you have a couple loose ones and a couple tight ones, you think that load's going to be distributed nice and uniformly? No, load always wants to go to the stiffest spot. And then, obviously, to prevent them from coming loose and falling. So how do these work? Why are we looking at this like tension? So think of a bolt like a spring. If you pull on that spring and let it go, assuming you haven't yielded it, it wants to go back to its original form, right? The bolts are the same general concept, except our pulling on it is elongating it by spinning the threads, right? We develop tension by starting to elongate the spring because we still are able to suck it down. You think of like a jack with our threads. Because our structural steel is stiff enough, it's not going to compress. So the bolt elongates, develops that tension, and it's locked in place with that nut. So that tension is always applied. Does that make sense? So it can never go back to its original length because we're holding it in place. So, how do we properly tighten a bolt? This seems very silly on the surface, but this is really important for these bolts to function the way they're intended. So you've installed all of your permanent bolts to a snug, tight condition. Snug tight is a very challenging thing to define. Our spec book, I believe, defines it as the effort, or the ordinary effort of an iron worker. So you guys can see how big I am. Right? I'm 5. That's a good question. We'll get there. Ordinary iron worker with a spud wrench. Thank you for adding that in there. So I'm about 5'10". But there's nothing that says I can't be an iron worker, right? Okay, got a lineman for the Vikings, 350, maybe. Is there anything that says he can't be an iron worker? Who do you think's ordinary effort is going to pack more force on that bolt, his or mine? His, right? So it's a really hard thing to define. So that's where we've said, you know what, take your 4-foot spud wrench, spin it on there. We don't want you to over tighten it, but get it good and snug with that spud wrench. Go through your entire connection, working from the inside out. Do that to every bolt. And because your effort maybe wasn't consistent, despite your best efforts, you're going to go through it again. Because I guarantee, just like tightening a tire, you're going to find a couple of those bolts have come loose. Right, so snug tightening is challenging. And we've had to go to putting this in the spec book that they have to do 2 passes to snug tighten. Simply for the idea of how a tire works. Right? So as inspector, you want to make sure that they've done their snug tightening procedure. This doesn't mean you have to be in the basket, but it's good to observe, are they doing it from the ground? Hey, are they working from the center out? Are Are they doing what they said they were gonna do? A lot of crews have gone to where they're using a 2-gun system because they're using these guns with lithium batteries, where they'll have a gun that is set to a torque that is significantly less than what it takes to fully tension these bolts, and then they'll come back with a second gun that has a rotation programmed into it that they know will get them to this tension. So when they're using the gun approach, it's great because they just pop that gun around, it's at 100 foot-pounds, boom, 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 go again, boom, 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 boom. Very consistent. We call it a precision bolting system, and we're really encouraging that of our contractors. So they snug it. You verified that they've snugged everything. Generally, you can go up and look at the splice, especially if it's got DTIs in it, and you can see that you can pick out the loose ones because the DTIs will almost shake a little bit, and just make sure that they're not all fully crushed. Then they're going to go through their permanent tensioning. Again, systematic approach, working from the center out, getting the DTIs to the spot that's been agreed upon and that's in the spec book. And then once they're done with that, you're going to go up and look at the DTIs, and we're going to dive way into what that inspection criteria looks like. So again, snug tight, the full effort of an adult using a spud wrench. We do, I guess we still say in there, minimal use of an impact wrench. It's not a torque force requirement. It's defined very loosely. I work on some national committees, and we still can't figure out how to define stuff. That just FYI. But really the goal is, when you think about it, if you want to bring everything into non-conflict, if you think about it that way, it makes a little bit more sense. So again, tire changing analogy, you're going to go in your star pattern, right? When you get back to bolt number 1, if this is your first pass, is bolt number 1 usually loose? Yeah, right? So the same thing happens in a splice. The other thing you could think about would be ironing a shirt, which I'm not very good at, but what I do know is that if I wanted to iron this shirt, I should start right here and work towards the body, right? I'm going to push that wrinkle probably right into here. I'm going to start in the middle of my shirt and work out the wrinkles right from the 3 edges. Bolted splices are exactly the same, and that's how you get those half inches. So the one project I was referencing, the contractor just started tightening from the bottom, working their way up. They did that because they didn't have a ladder. They were waiting for it to come. They didn't want to stand around. Would have been better off standing around for a half hour than 4 hours to replace the bolts. Right? And this is wrong. We do have the spec book updated, that it is required for multiple passes for snug. Just keep that in mind. Goal is to bring that connection into uniform contact, and this is essential for DTIs, because if they are not in uniform contact, you will be calling myself or somebody else asking, why are these stupid DTIs not performing? Probably with other choice words, because that's usually how I get the calls. Permanent bolting, we have requirements that this has to take place within 10 days of installing your permanent bolts. Why? Because the lubrication that's used on these bolts is water soluble. So you get a couple of really heavy rainstorms, you're going to lose a lot of that lubrication really quickly. And that's going to impact how these bolts actually perform. So if you go past 10 days, we require a number of bolts to be taken out of the bridge and subject to ROCAP testing to verify that the lubrication system and the bolts are still able to function. Really, there's very few reasons why they shouldn't do this within 1 day, but we do give them that. Our spec book talks a lot about when permanent bolting can begin on our diaphragms and any other lateral bracing cross frames. And we're going to go through some examples on this, because these, depending on the erection system, can wreak havoc on fit-up later on. But the big takeaway here is the girder splices themselves. We want them fully tensioned, permanently bolted, however you want to put it, as soon as practically possible, unless their engineering plan says otherwise. So these 4 categories we're going to dive way into, because this talks about when you can permanently bolt in your cross frames and diaphragms. But let's take about a 10-minute break. So why don't we come back at 10:20 on that clock right
I've been on my ground for all these years.
Yeah.
We have a tension of about 15,000 pounds. So we're not even close to our minimum of 39,000 pounds, which we're shooting for. So there's two things we can do here. The first being increase the torque setting on our gun, or we can lube the bolt assembly. In this case, we're going to lube it.
As you can see, the tension of the topside bolt is much lower than the bolt we pull straight from the keg. With a dry bolt assembly, most of the torque is used up overcoming the friction caused by the rust. Your efforts are spent fighting friction, not advancing the nut. The result is a lot of work, but loose bolts. This reinforces the idea that just because you torque the bolt, doesn't mean it's tight.
So the first thing we're going to lube is the washer face of the nut. About 40 to 50% of our torque is used up between the nut and the washer contact. Another 40 to 50% of our torque is used up between the threads of the nut and the threads of the bolt. Again, we're going to take our gun, still set at the 450 foot-pounds, hold my finger on the trigger, and we'll see what kind of tension we get. We get about 48,000 pounds of tension. We're above our 39,000 pounds, which is the minimum. By lubing the washer face of the nut and by lubing the threads of the bolt, we're able to more than double our load. As you can see from this demonstration, torque is not a reliable means of measuring bolt tension. We tighten 2 bolts and achieve 3 different loads because of the varying degrees of condition of those bolts. The first bolt we used was the 7/8
Does that make sense? So do you have any idea how much tension you have in a bolt? Just go by torque. No, you really don't, right? Now, so that's why MnDOT almost 20 years ago went to a DTI. Because a DTI essentially takes that piece of the equation out. The other piece of it is DTI frees up you as a resource to not be in the basket, right? Because if they're doing turn of the nut, folks are familiar with that, we'll go through it. You more or less have to observe them, otherwise you just have to trust their word. With a DTI, you can walk back to most of the stuff. But we'll go through some of that. Fastener installation plan. At least 4 weeks prior to starting steel erection, they're going to talk about the equipment, personnel, access, their snugging and tensioning procedures, and then a quality management plan, which is basically just how are you going to make sure that your bolts are being properly stored? How are you going to make sure you're snugging and tightening in the sequence provided? I'll note that you submit this as a draft. It's reviewed. You take conditional exception of it, but it's not finalized until the pre-installation verification testing has been performed. So what is PIV? PIV is a task that we're going to do 14 days prior to permanent bolting, prior to the work beginning. And we do this to ensure that all parties are familiar with the procedures. So you're going to use the same equipment that you're going to be using up in the steel. You're going to check the tools to make sure that they can perform and get to the load that we're looking for. We want to make sure that the bolt assemblies themselves still have the proper amount of lube. I mean, they really should be, because you're going to crack open the kegs for the first time and pull them out. But things happen, right? Sometimes these bolts can sit in kegs for well over a year. But we want to make sure that the bolting assemblies are still in suitable condition. And eventually, the goal of this is to expand the acceptance criteria. So our spec book has some very hard limits on what can be expected and accepted into the project. If you've been around DTIs before, they're super variable. They're highly dependent on your pinning and bolting sequence and doing that correctly. And even with a well-developed pinning and bolting sequence, you can still have trouble with DTIs. And so the goal here would be, let's use some new tools. Let's use more refined methods to expand that criteria so we don't have to reject as many bolts. I've been a part of a job where we rejected 20% of the bolts. That's a lot of money, right? When I would venture to guess, probably could have got that down to 5. but without having a reliable way of ensuring that we have the tension in the bolts, that's all we can do. So that's the underlying goal of this that we're still working on getting there. So what do you need to do PIV testing? You need to have a hydraulic load cell. That's that Skidmore Wilhelm device that they showed in the video. It's important to make sure that this was calibrated within 1 year of performing this test on your job site. So also make sure it's in good condition. I've showed up to a job site where contractor dropped the tailgate of his truck and it was very obvious this thing was flying around in the back because he didn't have it tied down. I'm gonna guess the calibration isn't good anywhere if that's all they were storing. So question those things for sure. You need to pick an appropriate sample size. So the spec book talks about a minimum, and I emphasize a minimum of 3 fastener assemblies that meet these combinations of diameter, length, grade, and lock. So this does not equate to just 3 bolts and you're done, because typically you do not have the same bolt length for your entire job. So does that make sense? You have to do 3 for every 2.5 inch, 3 inch, 5 inch, 9 inch. So on the Twin Ports job, where a lot of these pictures have been coming from, I think the first bridge, we had 10 individual combinations of bolts. So that was 30 bolts that had to be tested. So you can see how much time this could take, right? So it's important to make those separations. So we talk about doing the DTIs and doing the PIV testing. Let's watch a short video on that.
More boxes, more options. Grainger has over 1,700 box types in stock and ready to help you pack, store, and ship.
Hi, I'm Rob from Applied Bolting. In this hands-on clinic, we're going to be performing the pre-installation verification test. The pre-installation verification test is slightly different than the job inspection gap, which we do cover in another clinic. The pre-install test is done to ensure that all bolt assemblies, lubrication, installation methods, and bolt-up crews work together to achieve minimum bolt tension. Now we do this before installation because it is easier and safer to address bolting issues on the ground instead of up in the steel. Now the first thing we're going to need to do the pre-install test is a calibrated hydraulic load cell designed to measure bolt tension, such as our Skidmore Wilhelm here. Now it's also very important that your Skidmore or whatever hydraulic load cell you're using is within its calibration date. Otherwise, all these tests we're going to be doing are null and void. So the next thing we're going to need for this test is 3 bolt assemblies for every diameter, length, grade, and lot that will be found in the steel on your job site. It's also very important that we record all the data from all these tests. We do have a handy form that can be downloaded from our website at appliedbolting.com. For our test, we're going to use 1 fastener combination, a 7/8 by 3 A325 bolt, our squirter DTI, an F436 washer, and then our DH nut. And we're also going to be tightening this from the nut side. Now when we do our tightening, you can either use a hand wrench, a non-impacting hydraulic or electric gun, but for this we cannot use impact guns. So for the pre-installation verification test, no impact guns are allowed. Important to note when doing this test that regardless of the diameter or grade of bolt you're using, you're always going to be tensioning it to 5% above the minimum required bolt tension. In our case, for our test here, we have a 7/8 A325 bolt. Minimum tension is 39,000 pounds, so we're going to go 5% above that, which is 41,000 pounds. Now we're going to tighten our bolt assembly using our non-impacting electric wrench. There's 41,000 pounds. So now that we've hit 41,000 pounds, we're going to use our 5-thou feeler gauge and see how many entries and refusals we have. Now an entry is where the tip of the feeler gauge goes in and touches the bolt shank. A refusal is where it does not touch the bolt shank, even though it may go in part way. For our test here, we're looking for at least 1 open gap, but it's important that you look at your job site specifications to make sure you're doing it correctly. So there's 1 entry, a 2nd entry, a 3rd entry, 4th entry, and 1 refusal.
So talks about project-specific specifications, and we will cover that. Just note that what he's talking about here is different than what's in our spec. Okay? It's more to demonstrate the idea of what does the PIV look like, and then how do you perform this inspection. This is exactly what you'll be doing off of the steel.
So with this DTI, we have 4 entries and 1 refusal. We would do this test 2 more times and ensure that all 3 bolt assemblies have at least 1 open gap or entry. Now that we know that the bolt assembly and installation method works correctly, we can confidently put this assembly in our steel on the job site. If your DTI appears to be dead flat during this test, there's a few things you can look at before you go any further. Was your skid mooring calibration? Is the right size front plate and rear bushing in your skid mooring? Do you have the correct bolt assembly? Is there a 490 DTI with your A325 bolt? Sometimes the washers are too soft, and that can affect this test. So those are some of the things you can look at. If you do have any other questions, you can give us a call, and we can give you some step-by-step instructions to get through this.
Check this out. I'm going to show you how I afforded this car.
Okay. Any questions on that? PIV is required to be done in the field, so it's something that you'll need to observe. Certainly, if you need assistance on this, feel free to contact the bridge office. So let's talk about tightening methods for verification. Turn of the nut. This is the historic method that we use forever and ever and ever. We still use it on some applications, generally not our structural steel bolting overhead signs, though we still do. It's torque-based method, which is, I'm hesitant to say that it's a torque-based method. It's torque-based simply because when they originally developed this, they did a lot of testing around torque, but the reality is it's a vocationally based method. So lubrication and snug tightening are imperative for this to work, and you're going to see that we're basically just saying once you've rotated it so far after it's been snug tight, it meets that minimum tension requirement. So there's no measurement, right? This is empirical based on the length of the bolt. So snug tightening is super important in this case, right? We're going to skip the video on turn of the nut because more or less this picture does a good job of describing it. You're going to snug everything up. Depending on the length of your bolt, it's going to tell you how much return needs to occur. And you'll accomplish these measurements by match marking you can kind of see it when I pass this around, the tip of your bolt, the nut itself, and the steel, so that you can see that it's been appropriately turned. Does anybody know why we mark the bolt?
Stay on the backside.
To make sure that the bolt hasn't spun, right? Because if we're gonna go a third of a turn and the bolt turns a sixth of that, did we really get a third of a turn out of it? No, we didn't, right? So it's important to match all 3. Okay, I'm gonna pass this assembly around. This is installed in the correct order. One thing I will pass along with it are these feeler gauges. And so what I would like for you to do as it's coming around, just see how these would potentially be used. Obviously, you're going to have steel in the way, so you'll push your DTI against your nut and how you will insert them. Note that this particular DTI has these little bumps in it, if you will, along the perimeter. That's to help you locate where the feeler gauge is supposed to go. Not all DTIs have that. It's a pain in the butt when they don't. Just FYI. I'm going to pass around 2 feeler gauges as well, because when you get the DTIs, they will come from a separate supplier generally than the bolt supplier. And oftentimes you will get a packet in there that has 2 different thicknesses of feeler gauges. So you can take a look at that too. There's a 0.015 and a 0.005. For transportation structures, we always use the 0.005, no matter what the manufacturer says. I'll pass them both around just so you can see the very small difference between the 2. Again, this is our normal A325 bolt, which is 99% of the time what we're going to be using. DTIs, as we're passing this around, take a look at them. Tension based, right? Because the only way to crush these protrusions is by elongating the bolt and putting that compression into there. So these are almost always required in the Division SB. So spec book says here are your methods, but then the Division SB overrides to say you will use DTIs. And this big piece, and we've harped on this a lot, make sure that they're assembled in the appropriate order. Why do we use DTIs? They are more reliable than turning the nut, right? Because you can physically see that the protrusions have been crushed. And even if even if a bolting assembly is slightly loose when you started, they still can finally crush once you meet that elongation, right? Whereas rotation based, we have no idea because we don't know where it started. So they are more reliable. They tend to be more consistent. And then they allow obviously a lot of flexibility for you as an inspector to not sit in the basket and babysit the turn of the nut, right? Because we can go back and post-inspect them. Does that mean that you shouldn't watch the bolting operation? No, you still should be present to hear the different things, make sure they're following their sequence, but you don't have to be in the basket. Let's see, let's go through this one real quick. Watch the whole 9 minutes.
We're here today on the job site to demonstrate the proper use of direct tension indicators, otherwise known as DTIs or load indicating washers. The most common use of the DTI is to place the DTI under the bolt head, turning the nut to tighten. We will now demonstrate that for you. I will hold the spud wrench and observe the DTI as the protrusions begin to collapse. When I believe that they have collapsed to the proper gap, I will signal the operator to stop impacting the bolt. Go. There we go. Took less than 3 seconds to impact that. Visually, I can look at the DTI, see that the protrusions have been collapsed to the proper gap, and that fastener has now been installed properly. The second most common use of a DTI is to put the DTI under the nut, turning the nut to tighten. One of the advantages of using a turn short DTI is that it does not require the use of a hardened washer.
Which again isn't necessarily true, right?
Operating the impact wrench, I will also keep an eye on the DTI, again compressing it to the proper gap. Visually, I can see that this DTI has been compressed to the proper gap, and this bolt and nut has been properly tensioned. The third method of installing the DTIs was very similar to the one we just did, only the very critical that the bolts must first be snug tightened before final tightening. With DTIs, this is easily accomplished. The first partial tightening pass is in order to bring the plies into firm contact, thus preventing subsequent loosening of adjacent bolts on the second pass, as the plies will have first been fully compacted. By partially compressing each DTI, more than half the required final tension will be induced in each bolt. So for instance, on a 7/8 inch A325 bolt, that will be about 10 tons in each bolt. That should be more than sufficient to bring all the plies together. Work on the bolts at the most rigid part of the connection first, then tighten out to its free edges. DTIs are the only method where you can visually gauge snug tight. Now finally tighten by fully compressing each DTI as I have just demonstrated. Please remember to follow the rules for short slotted and oversized holes. Remember to cover the holes with an F436 hardened washer. Make sure the holes in the washer are normal size. Then place the DTI on the top of the hardened washer.
So inspection criteria, again, an active involvement, right? We're gonna observe installation and tightening, don't have to be in the basket necessarily with them. Then we gotta verify that it's been completed appropriately. So what does verification look like? The first thing, checking the stick through. Stick through would be the distance that the threads protrude beyond the end of the nut. Flush is okay. Slightly subset, start asking questions, right? Because they should have been sized so that they are flush. They get 1/8 to 1/4 inch of stick up. Okay, so this is usually pretty obvious. If you stand on one end of the splice, you can see the ones that are out of compliance. Okay. This is a pretty quick, easy thing to check. Inspection methods. The spec book talks about a calibrated wrench and a DTI. I'm going to simply let you know that the calibrated wrench is in here. It has to be calibrated if for whatever reason you're going to be using this. Generally, it's prohibited. But the big piece of this is you're going to establish a job inspection torque. That torque is not good for the duration of the project. That torque is good for that shift, and that's it. Keep that in mind. You may find that it ends up repeating itself from shift to shift to shift, but the procedure has to happen every single shift. Does that make sense? Okay. Oops, I'm sorry. Why are we calling that calibrated wrench? DTIs. Video did a decent job. I had to skip ahead a little bit, but did a decent job talking about this. Visual inspection, right? Make sure that we're not over snugging the bolts. And so we define over snugging as more than 50% of the protrusions crushed. Okay, so keep an eye on this again. For the most part, you can visually look and see if this has occurred or not. You have to make sure that the DTIs are oriented correctly in the correct spot, and that the contractor has followed their QC plan. They should come to you and say, all right, our snugging's done. We follow our procedure, will you go check it? This isn't something that you should be bird dogging. Once you fully tension, you verify the snugging, you're gonna go start by inspecting 10% of the bolts with the feeler gauge. And they should think about the 10% based on the area of the splice, just like the pinning and bolting when we're doing the erection, right? So the top flange is going to have its own 10% compared to the bottom flange compared to the west. You're going to insert that feeler gauge, always using the 005. And what we talk about is that we have a minimum amount of entries per the manufacturer, but MnDOT talks about that there has to always be one open. Always have to have one entry. So they can't be crushed completely flat. Caveat to this, we allow 10% of them to be completely crushed flat. Why do you think we do this? Any ideas?
Not overnight.
They're not over tight. Once they're all flat, do we have any idea if they're over tight or not? We just know that once they're all flat, they're minimally tight, right? Because the DTIs are designed to crush at whatever that minimum pre-tension force is from that spec book table. So once they're all crushed, we don't know if they're a ton over, if they're 10,000 pounds, or excuse me, if they're 10 tons over, 20 tons over, right? So that's why it's important to MnDOT that we allow for one entry, because this allows you to be out of the basket. Now, contractors will often struggle to maintain this because the DTIs are designed to crush at that point. And as you can see, if you're not the one operating the gun and looking at the DTI at the same time, it's hard to see this happen, right? So I've been on a project once where the contractor said, hey, we're doing everything right. And these DTIs are all crushed. I said, all right, demonstrate it to me. So we go up, they snug an individual bolt, we check it. This isn't a splice that's completely done. I said, all right, tighten it. They hit her for 3 seconds is what we agreed to. We look at it, and they have 2 entries, so it didn't meet the minimum for the manufacturer. And I said, all right, put your gun on there and just pop it. So, pop, all of them crushed flat. So that's how precision these DTIs can be. And that's why it's really important that you're observing the contractor, because I wasn't there for them to say, yeah, these last 600, that's exactly how we did it. Right? I'm taking their word at that point. But they demonstrated to me that, hey, these are being that finicky. So we compromised by picking about 10% of the bolts in the connection and redoing them using that same procedure to verify. That's a lot of work, right? That was about 2 hours worth of effort. So these things can be really finicky. I will tell you that since we put in the spec book the multiple of 2 passes for snugging, that problem has substantially gone away. It comes up from time to time, but it used to be almost every steel bridge, we'd get calls on this. And last year, we got a call on one. And it was partially because they were using the wrong size bolts. It's really important, that snug tightening procedure. I can't emphasize that enough. So again, you're going to inspect 10%, and you're going to increase your inspection rate up to all the bolts based on how many rejections you find. So again, the manufacturer is going to state the maximum. We're going to state that you have to have a minimum of 1 entry. They can remove.
Nick, I think you might add a question.
Oh, yeah, I'm sorry. Yeah.
Yeah, I was just want to add with the one thing, why can't we cannot achieve that? I mean, try to cannot achieve that.
So that's that partnering piece. Like, if you can see that they're putting that good faith effort in to try to achieve that, and it's popping back nicely, that's something where I'll say you can ignore this 10% and allow them to go above it. The hard part is if you don't observe that, for all you know, they were sitting on every one of those bolts for 10 seconds, right? When in theory, we saw them do a 3-second pop and then a half a second pop, and that's what crushed it. But we don't know, right? That's where they have to demonstrate and build that confidence with you. Does that answer your question?
Yeah.
Okay. Thanks, Paul. So let's say that they're at 15% completely crushed. Our spec book does allow them to just remove down and replace enough to get them within that 10%. So just because they've gone over doesn't mean that they have to replace all of them. We give them that flexibility. Does that make sense? Okay. Certainly, if you have any of them that are not tight enough, you're gonna retighten and retest. If the feeler gauge, again, is refused in all of the openings, you can remove and replace like we talked about, or demonstrate the procedure again to show that good faith effort like we thought. So this is all in the spec. This expanded criteria, we can accept this with a well-documented PIV testing and these precision bolting systems. So just as an example, for the Twin Ports project, we partnered with that contractor, and they did a very thorough job of pre-installation verification testing. And so we allowed them to establish job-specific criteria for certain bolt lengths. And partially it was because they were using a 2-gun system, so we agreed on a torque for snugging and a certain amount of rotation. And because of that, we accepted quite a few bolts that were completely crushed. We also accepted quite a few bolts that didn't meet the manufacturer's minimum amount of entries, or minimum amount of refusals, excuse me, because we had done enough tests to prove to ourselves that the DTIs were performing as intended. So that's where this PIV can be really useful. And it's important to document all this up front, because if you start having problems, you can rely on all of that too. Does that make sense? We're going to work through a quick example. This is in your appendix. You can also get most of this information off of your plan set. So if everybody could, please turn to your plan set. So the first question, what span is field splice 1 in and what sheet can you find this information on? Span 1 in sheet 8. Anybody confirm that? Anybody disagree with that? And I'll flash this up on the screen in a moment here. How far away from the center line of the field splice is it to the down station bearing? 39 and 3 inches. Does anybody disagree with that? Okay, so if I flash this up on the board, we're on sheet 8. Identified in the elevation and the plan view, location of the field splice. We know that this is the field splice. Field splice spacing. Right? You can trace over where that line is. I'm not familiar with this at all. So you had two dimensions you could have picked from. 70 foot 6 inches or 139 3 inches. Why did we pick 139? Down station. How did we know that direction was down station?
Always left to right.
Generally it's left to right. I caution you on saying always because we had a consultant that had never done a MnDOT job before, did all their plans backwards. Nobody caught it. So, how would we verify that?
Find out where the bearing reduce button,
Right, so you're going to be able to find the stationing generally on your working point layout or your sheet. Does that make sense? So we have a pier strut on 35W that was supposed to be built that is a slope like this because the roadway was going down. It's backwards because of that. Because nobody got it. Not the end of the world, but it costs us a little money. Okay, with that plan set out, what sheet in the plan can the field splice bolt information be found on? Sheet 14. Anybody else verify that? Does anybody disagree? What was that? Bolting information. This one's a little bit of a trick question, right? Because I emphasized that the bolt lengths and the washer configurations are all going to be found in the shop drawing, right? But you're going to be able to figure out the number of bolts and the arrangement of them per field splice in the original plans, right? Because the engineer record has to decide how many bolts go in there. So, a little bit of a trick question. If you flip to sheet 14, this is skill details 3, you'll see a splice plate elevation. And then there is a very generic sketch that gives you letters that you can come down to this table to figure out how many bolts are in each part of the connection. Again, you're not going to get the bolt lengths here. Okay? So this particular list, I kind of alluded to it already. Where are you going to find this? What document that's showing up there? Yeah, the shop drawings, right? So, if you were to take this, we're gonna skip this exercise because it's kind of just mathematic gymnastics. If you were to take this particular bolt list, go through the inspection criteria, you would be able to do so. So let's at least do part of it, I guess. We're not gonna worry about the numbers part. What is the number of drift pins required in each component? 25%, right? So if you were to flip back and we were to look at the top flange, we're figuring out what 25% of 48 is, right? What's the number of snug tight direction bolts required in each component? Again, 25%, right? What is the minimum number of BCI washers that must be inspected? 10%, right? So you could go off the table for the top flange, right? Here's the spec reference and the numbers to go along with it. So you'd be able to go through that particular table from the shop drawings and develop this for yourself, right? Or you could use the plan drawings because this is just purely quantities, right? We're not verifying things. Does that make sense? I'm very confident everybody can punch numbers into their calculator. I'm more concerned about you being able to find the information. Is there any questions on that? Okay. We're done. We got the girders hung. All the bolts are tightened. We're done fighting about DTIs. We can move on to something else. That sound good? It only took us 2.5 hours. That's not too bad. So, shear connectors. These are installed after the decking is in place because they're a tripping hazard. And yes, the shear stirrups that come out of pre-stressed beams are also tripping hazards, but we don't post-install them. This is an OSHA thing. So they're installed generally by an automated welding process. So when they use the automated stud gun, you don't have to have an AWS certified welder. Generally, you're going to have it anyway because of the way the unions work. They have to be installed on dry flanges and above 0 degrees. Okay, otherwise the weld will not work. It's important that surface prep removes any sort of prime coat that's on there, any mill scale, rust, anything like that. Or again, you're not going to have a good quality weld. I'm going to pass around a Nelson stud with the ferrule around it. Go ahead, make sure you take a look at the little dimple that's on the bottom too.
So they go through and grind all those locations?
Yep. Yep, they got to do that after the fact. So you can see they've got it all chalked out and they're gonna grind off those spots. That arc shield or ferrule has to be kept dry. That's what's going to protect the weld. If you think about if you've done any sort of like gas shielded welding, that's performing the same function, right? To protect it as it's cooling. These, if they do get wet, they can be oven dried just like welding rods. And the spec book talks about those requirements. So generally just keep them dry. That's the better way of handling these things. So how do you inspect these? We don't want to look at welding, right? It's dangerous for our eyes. So we observe what's going on. And so you're going to visually inspect the installation of the first 2 studs, which really means that you're going to be nearby, listening, if you don't have a welding mask on, to how everything's going. Does it sound like the machine is functioning properly? Does it occur quickly? I mean, are there anything that seems out of the ordinary? Once the weld has taken place, you're going to go down and look and see. You can see all these black lines. That's from the arc flash occurring and creating soot. Are they all the way around that stud? Once you break the arc shield off, does it look like a good, nice quality weld? Because it should. It's an automated process. That's what we're going to observe, right? Not the actual welding itself. Once we've made that observation and it looks good, this is where you let them start going. Again, kind of looking for those general things along the way. You're talking about putting thousands of studs on. Do we expect you to look at every single one of them? No, but it doesn't take that much effort to walk along and look for things that aren't consistent, right? Once they're starting to be installed, you're going to strike the head of them with a maul 1 out of every 100. This is pretty easy to walk along. And when I say strike these ones, you're going to bend them over until they're 30 degrees. This tests the performance of the stud itself and the quality of the weld, because if the stud cracks or the weld breaks, then we know we have a problem somewhere else. If it happens to be below freezing, you gotta do 2 per 100. How do you pick these? By doing that visual inspection. If you see spots where you don't have that weld all the way around or it looks poor, those would be ones that I would suggest striking. The other thing that I like to do is I'll walk along with that mull and I'll tap them really, really kind of lightly. And you'll hear a kind of more of a dull ring instead of a nice ping for the ones that have problems. And those are the ones I would hit, right? We're not picking on the contractor, we're taking out the poor quality material. Does that make sense? Because if these aren't attached right, the design doesn't work as intended. So use your discretion as an inspector, but again, the minimum is 1 per 100. Yeah. No, I mean, it just kind of depends. I'll usually kind of walk through and almost do like a diagonal pattern, just weave it back and forth, just so it's randomized, right? I try to not mimic. I mean, usually, I shouldn't say. Oftentimes you'll see these guys kind of go in a snake pattern to install it. I'll try to not follow that same pattern in case there's something different with how they're installing stud number 3. Or, you know, right? I mean, you want to be random as best you can, but certainly pick on ones that look odd. We don't want them in the structure.
So I see it says here in the spec that it's after the belt cool, so on a normal summer day, how long would that typically take?
This is a really small well.
I know, but
And
it's
really thick.
really hot too.
Couple minutes. It really doesn't. It's not that long. I mean, you want to get far. It's a trade-off because you want them to be far enough ahead of you, but then you don't want them to be too far in case you find a whole bunch of problems. Right? But it generally doesn't take that long. Yeah, I'd say 5 minutes is probably the longest you're ever going to have. So again, you're looking for visually poor weld, listening for the gun malfunctioning. Certainly if the weld ruptures or dislodges from the flange, or if you crack from the shank, you're going to remove, replace, and you're going to increase your inspection frequency, right? Because there's something. The length of these, so with steel, unlike concrete, so we still have our stool or our haunch. And that's that gap of concrete between the bottom of the deck and the top of the flange. Now we detail steel such that that stool height is constant from the top of the web to the bottom of the slab. But your top flange can vary in thickness. So the amount of concrete thickness is going to vary. And because of that, your stud heights can vary. And so even though this will recommend a height in the plan, so if you dig through your plan, you'll find this exact image where it's calling for a 7/8 by 7-inch tall stud. This can vary, right? We have a tolerance for our stool heights. The beams may deflect a little bit different than they were designed. So it's important to get the stool shots done. If the contractor goes and orders all of their studs anyway based on this, they're liable to potentially have to change that. That has happened because we do require that these shear studs are engaged in the lower mat of steel. And so you can see how this head is up into the bottom mat of steel here. And this is probably more common of an issue on pre-stressed beams because we can't control the camber as much. But they do have to be up in here. And if they're not, we need to mitigate that. The other piece is they have to be below the top mat of steel. Because at some point in the future, we might come mill off 2 inches of concrete and we don't want to clip all the heads of the studs. So they have to be below the top mat of steel as well. And that's where you can potentially get yourself into problems. So what does that look like? Think about a plan view. You've got your bottom mat of steel, and your heads are projected up in there. This can become an issue with really steep cross slopes, like if you have a 6% cross slope through here. The flange is still flat. We don't build the flange at the cross slope, so your stool height varies from one side or the other. Because I've been on a project where this flange is 48 inches wide. If you think about that over 6%, your stool heights can vary quite a bit. So that's what it looks like ideally. But in some cases, you may end up with a taller stool. So what do we do? If they have not yet installed the bottom mat of steel, they potentially can remove and replace. They're not going to want to do that. If they have installed it, our options are a little less because they potentially have to untie all that bottom mat of steel. So Corrective action 1, if they have enough clearance to the top mat of steel, they are allowed to weld 1 additional stud on top. I think the Nelson studs come as short as 3.5 inches, which generally will fit between our 2 mats of steel. So this is oftentimes what we see them do. Corrective action number 2, if that dimension doesn't work out, they can tie in these hat bars. This is pretty common practice. Sometimes these are Z-bars because they put a lap splice right here so that they can feed it in underneath. This is pretty common. If either of these situations come up though, you want to get the engineer of record involved so that you can understand what the appropriate spacing is. If they're too tall, we do not allow them to just grind the tops off and get to the right elevation. Does that make sense? Moving on to field welding. Permanent field welding is limited to pile splicing, expansion joints, shear connectors, unless it's documented in your plan set. Minnesota is pretty much a no field weld state, purely because of the quality control piece of it. Doesn't mean it doesn't happen, but we try to avoid it in these high stress regions. Temporary welding, there may be a need for a contractor to do some temporary welding on our permanent fixtures. We generally disallow this, but should it come up, should it be necessary, it needs to be approved by our engineer, and that has to be completely removed by grinding. There's a lot of criteria behind this. Regardless, it has to be performed by an AWS certified welder. Within the spec book, it talks about area A. So you remember our continuous beam versus our simple span beam. Area A is going to always be that top flange that's subject to tension under dead flow. So it's permanently in tension. It's going to be defined in your plan set. So folks, open up your plan set, find an elevation view. I think the first one starts on page 8. And identify. Can somebody tell me what area A is, what the length of this is in your plan set? I'm on sheet 8, so we're all looking at the same dimension. What's the dimension of area A? 146 or? There you go. Good job. Yep, so on sheet 8, it is 146 from a point in the span to the center line of bearing. Then flip to sheet 9, and it goes an additional 100 feet into the next span. Yes, 246 is the correct answer. Nice work. So that's the area where no field welding is allowed, unless it's in the contract plans. Very important because that can represent potential fatigue issue long-term for the bridge, which may result in the girder fracturing at some point in its life. We don't want that. Fracturing girder can't carry it. The exception to that, well, let me back this up. This is in area A. Are any of these welds permissible? There's 3 different types of welds here. Are any of these permissible in area A? Stud welds, yep, these are. How about the screed rail? Is this one permissible in area A? No. How about your overhang bracket? Coil rod, right. None of these are permissible in area A. Contractor has to come up with a different way of attaching their supports to the bridge, even outside of area A. Do we want these bolts here? No, we really don't. The spec book does allow for a 1/4 inch fillet weld that's not longer than 2 inches. So that's in this formwork section of the spec book. So visually, this looks like this is more than 2 inches. So we want to allow here. In theory, this one might be okay. So that's where a lot of these contractors get really creative. It is permissible to weld a bar between these 2 studs and then weld your screed rail support on top of that. Because you're not on the structural steel. worry so much about that one. I would worry about the quality of the welds that are on our top line, regardless of where it is. Bad welds, when subject to tension, crack. Cracks turn into fractures, fractures turn into bridges sagging. Does that make sense? So generally, if they want to get the welder out and start welding on the bridge, stop them and ask a lot of questions. All right, we're done with girders. Bearing assemblies. 3 basic types: expansion, guided, and fixed. Let's walk through these. So an expansion bearing allows, well, first let's think about a bearing in general. A bearing is to help collect all of the load that your beam has accumulated and bring it into the substructure. Now we know that our beams and our decks move because of heat and because of other things, right? So we have to accommodate that movement somehow, but we also have to keep the bridge from walking away from its substructures. That's where bearings come into place. So we have expansion bearings. The way that we do these in Minnesota is we allow movement. If it's a true expansion bearing, it's movement in any direction. So both back and forth, in and out of the page, diagonally, but it's always in a horizontal plane. We don't want them moving up and down because that means our substructure is settling or our beams are lifting up. So that's an expansion bearing. We allow rotation oftentimes to happen through that bearing. That's why if you've seen a MnDOT bearing, typically it has a curved plate. Because as a load comes onto a beam, it wants to deflect down. That also has to have a component of rotation. So we take that through the curved plate. So that's an expansion bearing. Free to move, horizontal. This is what it may look like. You have a sole plate. This happens to be a pre-stress beam, that curved plate for the rotation. We have a bearing plate to help distribute that load out into an elastomeric pad. This pad flexes back and forth to accommodate that movement. But we still have to get all of that vertical load down into our beams. Because this pad is not constrained anywhere, it can move in any direction, right? Because the bridges, even though we put the expansion joint thinking they're just going along the beams, the deck breathes side to side too. A fixed bearing. On a bridge, the vast majority of the time, fixed only means fixed from movement. So if we still allow it to rotate, but we're not allowing that beam to move without taking the substructure along with it. So generally the substructure is way stiffer, right? Especially in the buffing, because you'd have to move all that soil. So fixed bearing means we're holding the superstructure in place at that location. So fixed bearings are going to end up taking load, horizontal load, and putting it into the substructure along with the vertical. So no movement at a fixed bearing. Does that make sense? That fundamental difference. This is what they're going to look like on a typical bridge. You'll still have your sole plate, you'll have your curved plate, you'll have a much thinner elastomeric pad because it's not expected to move back and forth. And we establish fixity through an anchor rod that goes through that bearing plate and connects into the substructure. So that's our fixed, not moving bearing. This is what they kind of look like. Pretty simple. Generally, these holes are drilled and grouted post beam erection because we do want to give them a little bit of wiggle on the side. Because we're doing this post concrete placement, we got to make sure that we have at least 2 inches of clear distance between that anchor rod and the reinforcement that's been embedded in that substructure. Again, that number 11 bar is that big for a reason. We don't want to shave the steel off of it. So they should have provided a template. You want to make sure that the girder is in that final condition. Again, we allow them to move it a little bit. We're pretty loose on our girder placement tolerance, but keep in mind that if you let them move that girder 2 inches over, and we said you have to have 2 inches clear, you're probably violating that if you installed it for a template, right? So if that rebar is encountered during drilling and coring, you got to contact the engineer to figure out what bar it might be and what the next mitigation effort is. This is our typical detail. So we're going to embed an 18-inch rod in. We have just a little bit of stick up. This number is detailed on the plans. It does vary a little bit, which is why it's not shown here. But you're going to core this in and then you'll put grout to fill that hole. Now, what's important about this is you got to give a little bit of consideration to cold temperatures, right? We talk a lot in the spec book about cold weather concrete, but we're pretty quiet on some of these anchor rod details. So if it's 10 below zero, how warm do you think that substructure concrete is? It's probably 10 below zero, unless you just got done with the pour, right? Do you think that grout's gonna set up when its insulation is 10 below? No, so if your contractor is gonna be doing this grouting in cold weather, they may have to get out there the day before to heat up that concrete mass so that your grout will cure and not all fall apart. So give consideration to that, because the spec book is not real tight on these elements, but it's something that we do care about. The other thing you gotta kind of look for, and this happens to be a plan here, right? So they're getting ready to set a beam here. You can see how it's nice and open, and even with the beam here, it'll be somewhat easy to core, right? This one, this got detailed wrong. Normally this hole would be offset from the diaphragm, but you can see we're not gonna get a core bit through here with the diaphragm in place. So generally this is avoided, but it's something to kind of keep an eye on, right? We ended up having to go remove all of these diaphragms to put that anchor on it. And rework, right? This was a cost of MnDOT because it was a planker. We have high load multi-rotational bearings. These are going to typically be pot or disc bearings. These are going to be reserved for your very heavy loads, long spans, things like that. Not super common to see, but a couple things. There will be an estimated height in the plan, but because these are proprietary elements, the final height of those is not known until you get the shop drawings. Because of this, 9 times out of 10, you're going to have to get revised sheets to establish the correct beam seat elevations to account for this new height. So, biggest takeaway here, if you're getting ready to pour your beam seats and you don't have revised sheets, start asking questions to make sure that the bearing height has or has not changed. Right? Always good practice when you have these high load bearings. So I don't know that I've ever been involved in a project where those seat elevations have not changed. And it may not be, right? I mean, that is entirely possible. But it's a good check to make before you place the bearing seats. We do try to highlight that with the plan. These are also, because the loads are significantly higher and you're using a larger anchor rod generally, we place a grout tube instead of coring through it to place the bearings. So again, making sure that you understand the grout tubing and blockout detail, and that we're placing these bearings in the correct spot. They did have a project come up, there's this coupler here, things got a little bit wonky, and although the threaded rod could fit in here, the coupler couldn't. So we ended up having to go through and chisel out a bunch to try to get these things fit because they had erected too much of the steel to come back and ship it. So keep in mind, some of these really small details can turn into really problematic things to deal with, especially if the steel's already loose. This is what the disc bearing looks like. You can see a much more robust system. But I think just for scale, from this bolt to this bolt, I think is about 3 feet. So significantly larger than what our normal bearings will be. This bridge had enough of a grade where the sole plate, this was a little different, the sole plate wasn't welded on. The sole plate's at a taper to accommodate that grade. That's bearing assemblies. So fixed ones can't move horizontally. Expansion ones can move horizontally. Do any of them move vertically? Hopefully not. Ironically, they do. So because I do a lot with our maintenance forces too, sometimes the loads get so light on these things that those elastomeric pads will walk around, either because they're getting cold when the weather gets cold, because they get really stiff, or there's enough vibration where they'll wiggle around. So we put these little keepers on the bottom of our standard bearings now to at least force everything to go along. But we do have them walk out on us. I've been out on sites where the pads are laying on the ground, the beams being held up by the deck. Ideally, you catch that before really heavy load hits. Measurement payment, just to briefly touch on this. Here's a list from the spec book. You'll notice that we're generally paying for things by the each, the linear foot, or the pound. You have to be a little careful about steel because of those longer procurement times. Oh, I'm sorry, I'm getting ahead of myself. So, steel is paid for, if you look at structural steel, steel is paid for by the pound. And in a typical project, that payment includes procurement of material, fabrication, shipping, installation, right? Is the same contractor doing all of those things? And what I will tell you is on a typical steel bridge, from the day it's awarded, the earliest you'll see that steel show up on the job is a year later on a typical project. So, it's costly to bring in all of this material, right? And the fabricator, in theory, has to float that bill for the whole project. It's where we allow material on hand payments to occur. And so, really, if the contractor is requesting this, it's very, very common. That request needs to be accompanied by invoices with heat numbers, test certifications, and all of that stuff should be stamped by a structural metals inspector. Because really what that metals inspector is doing is not only verifying that all of the specifications are satisfied, but that that steel is actually at the fabricator's facility. Because we're not floating them the loan to get it. They have to do that piece themselves and then be paid back. That's the material on hand. Very, very common request, but it needs to have all of this documentation along with it. Because of those long lead times, sometimes the state, or the owner, will have two separate contracts. We'll have a early materials contract, and then we'll have a construction project. And so this is where your pay items will delineate some. If it's an early procurement, it'll be a contract to furnish. And that's going to pay for the fabrication and the shipping to some site, whether it's, we've had jobs where it's gone to a MnDOT truck station because we know they're not going to be far enough along on the bigger construction projects. So you'll have a furnished pay item, and then you would have an erect or install pay item because you get two different contractors working on two different contracts. So be mindful of this. This example plan, 69-129 had a part A and a part B. I've only given you the part A of the contract, which is why it's only 27 pages to construct a 1,000-foot bridge. Right, so hopefully that makes sense where pre-stressed beam bridge that's 200 feet long, 260 feet long, has 62 pages. So you got a part A and a part B for the steel example. Keep that in mind. Really quick sidebar, because we have these overhead sign structures that often occur. They have a slightly different tightening procedure than what I explained for steel beams. What's really important about this is that it is very defined process of what they need to undergo. I don't want to walk through that because these handbooks are very well laid out. The forms you can pretty much follow along as you go. I more want you to be aware of this is a reference material that you're just going to need to study before you do this type of work. General tightening procedures, the equipment, it's all the same as what we talked about. It's just this has a very specific procedure that sometimes gets updated, so keep this in mind. We have all these forms out on eDocs, it's a nice handbook. This was all based on research from Iowa State in collaboration with MnDOT and special equipment. And this all came about because these signs were not getting tightened very well. Now, these signs, the primary load that they see is wind gusts from trucks running underneath them. And if you don't have tight bolts, those bolts will loosen themselves over time rather quickly. And I don't remember if it was a high mast light tower or if it was a sign that was a little bit taller mounted, but the maintenance crews went out to look at it because they got a report that it was moving. And these anchor bolts will stick up about 6 inches from the base plate, and the nut was at the top of that anchor bolt. So it was only going to be a matter of time before the nut popped off that, and then hard to tell if the structure stayed stable. So it's very important that these be completely tightened and following these procedures. And again, they're really well laid out, so I don't want to use your time. So quick review. This is now on Mentimeters, so let's see. Yes. Yep. So go ahead and get logged in quick.
And then we're next one.
I just hit advance, right?
Yeah, I think I was struggling with what to do, but I think we did the right button there.
Does anybody still need the QR code? Get it rolling. Close the door.
QR code or just type in the MnDOT code. Everybody in?
Heat straightening is permitted on steel bridges, true or false? Okay, overwhelmingly true. That is the correct answer, with the caveat that it has to be approved by the engineer once we've accepted their plan. Right? But we do permit it. In fact, when we get our bridges that are in service hit by an overheight load, very often we're going up there and just versus, especially if it's a steel bridge, versus cutting the girder off and replacing it. Which spec requires the contractor to provide false work plans and calculations to the engineer for structural steel erection? False work. That's it. 2402 3D temp works. Point 3B handling and storage, or point 3G the connections. Overwhelmingly temporary works, right? That spec's going to detail when it's required and what the submittal requirements are. Most common high strength bolt type is an A490, an erection bolt, an A325, or an A307. See, we have a pretty good majority, but just as a reference, this is something that you would be able to find called out in your structural steel notes. 490s are a very high strength bolt that sometimes will be incorporated to reduce the number of bolts or the diameter of them. And a 307 is what you're going to find in some of the more minor components like metal. Diaphragms in a bridge fabricated under full assembly have what size bolt holes? Standard, an ovular, an oversized, or a slotted. So again, full assembly bolt holes in diaphragms. Overwhelmingly the standard size hole, is that correct? So how much bigger is that, the bolt diameter? 16. And if it was an oversized hole, how much bigger is it? Right, good job. Primary function of a shear stud is to increase the reinforcement in the concrete slab, connect the beam to the concrete slab to make a composite deck, eliminate some of the reinforcement bars needed in the deck, or prevent the reinforcing bars from moving during concrete placement. So we got a good handle on that, right? It's to make that composite section where the deck and the beam work together. Now, an added benefit of it is we absolutely encourage the reinforcing bars to be tight in some locations so that they're not slipping around as much. But that's not their primary function. Which bolt tightening method uses a device that looks like a washer to ensure proper tightening by monitoring the flattening of the device protrusions? That's a lot of words to say what's hopefully a pretty simple term. Is it a turn of the nut, a fillet, a DTI, or a groove? So we overwhelmingly got the DTI. Hardened washer is required between the structural steel and the DTI when the hole is oversized. True or false? True is the correct answer. Right? We don't want that DTI to get sucked into the hole. Welding on a steel girder is permitted when? In area A, when the weld is greater than 4 inches long, when shown in the contract plans, or when completed by a MnDOT certified welder. It's only permitted when it's shown on the contract plans. So if you think about, just to take a little sidebar here, we have a weld detail in the back of the plans. It's usually B201 or 202 for the pile splices, right? So that is a weld shown in the plans. The expansion device sheets also have welds shown on how to complete that work, particularly if it has ball strips, right? So that would be an example of welds shown in the plan. In area A, we're not going to permit welds, right? And then there is no such thing as a MnDOT certified welder. There was, I think, 25 years ago, but we don't have that anymore. So if you have a welder shop with a MnDOT card, they're asking for their AWS cards. Beam seat elevation tolerances are based on the beam type, the fabrication assembly, the mood that the foreman is in, or answers 1 and 2. So answers 1 and 2 are correct because I know this emphasis was on steel beams, but remember we got those pre-stressed beams too, right? So the pre-stressed beam and the line assembly for steel girders fall into the same category, and then the full assembly is in its different category. Does that make sense? Okay. Bearing assemblies are used to transfer vertical loads into the deck, transfer lateral loads to the expansion joint, or transfer vertical and lateral loads into the substructure. So you got that one? Remember, load can't transfer through air, so the expansion joint doesn't see movement loads, right? It sees loads from the cars hitting it, but not loads due to movement. That's it. So I know that was a lot, and I will say I apologize for doing a lot because MnDOT does so few steel bridges. But at the same token, as Paul mentioned, I've been with MnDOT for 15 years, and some of my biggest problems have been related to bolting on steel bridges. So the more we can get the knowledge out, the better. And the biggest thing is you have a resource that can help you get through these things. Because the more you talk up front with your contractor and their team, the smoother bolting's going to go. Is there any questions? And I realize I'm between you and lunch. Is there any questions? Paul, what time would you like them back at?
Okay, thanks, Nick. Let's come back at 1 o'clock.
Thank you all.
Thank you.
Sorry, involves some maintenance contracts. One of them in particular being the bridge repaints. So 24, 78, and 79 were blended a number of years back, and most of what we'll discuss here today involves field repaints. So 2478. So the whole purpose, right, is to isolate and protect the steel from our very naturally corrosive environment. Also provides a aesthetically pleasing appearance, especially if you're in larger communities. They like things to look very pretty. Think of corrosion as like an electrochemical process. You've got an anode, cathode, and an electrolyte, a metallic path to follow. It's kind of like a dry cell battery. Our environment, combined with the very wet environments, as well as how's that? See how many times I can adjust it. So we'll touch through a few of the definitions here, especially dealing with coating thicknesses, coating systems themselves. Duplex simply implies two coat, so usually a primer and a top coat. We'll discuss hold points, and hold points are basically points during your inspection process that enable you, the inspector, to kind of take a pause from the contractor. Time is money. Everybody wants to just sail right along, and these hold points were put in as a way for you to check certain processes before the next thing gets covered up. Because you're painting, it's multi-coat. If they come in and they have their intermediate coat on before you got a chance to look at the blast or the stripe coat, much less the primer coat, you have literally no idea what's underneath. So we'll touch more on them as we go. Another one being the quality manual is as it states here, I don't want to read a lot verbatim, but it is a written document prepared by the contractor now that describes the policies and procedures that ensure and verify that the coated structural steel component will satisfy contract requirements. So basically, it's your go-to document for what happens if this pops up in the field, what happens if that pops up in the field. I'll show you examples as we get down the line here a little bit. And we have a sample of which you can work with your contractors if they're not sure how to do one, what one should look like, here at this web link. I would recommend it. It's good reading. I don't know if you can see it or not. Is there a pointer? Yeah, right there. Download it, keep a copy of it. So in your quality manual, you're going to have a custom procedure for measuring thicknesses according to SSPCP A2. So they can, at that point, say, once the primer has been applied, according to manufacturer guidelines, which they should have all this information too, I'll touch more on it as we go. But they will state how many measurements, what square foot area, any information you need to know if it's going to be a multi-step process. All the information can go right into this document. That way, no matter who shows up from your office, if you aren't able to make it one day and somebody has to sub for you, all they have to do is refer to this. It's spelled out for them in black and white. And this should be in your manual part, so you can just kind of look through this. You are to have the contractor submit their quality manual, let's see, 60 days for initial approval, 30 days for, it's kind of the cutoff for any final stuff, any changes they want to make. And it is required to be accepted by your entity and the contractor 10 days prior to even starting work. Let's see, SSPC QP1 is often overlooked or missed by just about everybody. It's a requirement for all field applicators. It provides documentation showing that the applicators, the people in the field working for the painting company, actually know what they're doing. That they've been trained using the specific coating system that you're going to be applying. Also in your quality manual should be references for a non-conformance report form, how SSPC PAT will be documented, any request for deviation, color drawdowns from the Lanetta chart, which is basically just a color sample swatch on a piece of paper if you've never seen one. Also with that are names of employees, including their job titles. This is important because like it's mentioned in the manual that the foreman of the job, say, cannot also be the quality inspector. There's conflict there. It's spelled out in black and white. Some smaller outfits, they tend to do a little bit of everything. So if the job foreman is also doing the QC, that's actually by spec not supposed to be happening. We've pretty much gone from doing the actual field measurements and everything to just kind of providing oversight. This has been basically pushed onto the contractor to provide how they're going to do it. I used to actually go into the containments, take all the measurements. I'd have my own notes, compare notes with the contractor. This is supposed to save time. So your assurance inspector, they are supposed to have knowledge of paint processes and procedures. You will make sure that the contractor is adhering to that quality manual and the specs. So a lot of what you'll end up doing is inspection of their surface prep, checking to make sure the containers are actually what they're labeled to be, observing blasting and painting operations, and with that especially is monitoring atmospheric conditions. With that required and make sure the contractor is providing adequate drying time between various coats and final inspection. You get what you inspect, not what you expect, right? If you just expect them to do it without you just kind of checking in on them, you may be surprised what you actually end up with. Keep all your files. Certifications, tech data, MSDS sheets, project records. Blasting residue is a big one. You want to make sure any blasting residue documentation you receive from the contractor or a waste hauler later on, keep it. Audits aren't pretty. You don't want to be a part of one. And if you are audited, it's one of the first things they're going to ask for is, what did you do with the waste? So to reiterate, paperwork of the disposal, highest priority of any concern on a paint project. Because you can end up with hazardous waste. PCA and folks get a little edgy when it comes to hazardous waste. If, let's see, some of them are gone now. Feel free to contact the Office of Environmental Stewardship. There's been a little turnover up there lately, but they do offer just-in-time training. More often than not, they are willing to come out to you, visit your job site, and they'll go through all of this with you. As far as what documentation you need to have, the process in which it's going to go down, and best methods and practices for testing, sampling, if it needs to be done, as well as on-site storage and final waste disposal. Y'all get involved in some dirty work. Paint projects, believe it or not, can be pretty dirty, pretty dusty. So you're going to want to make sure you've got all your PPE, any breathing apparatuses required. Let's see. One big thing, if they end up having to heat any painted metals, any torch cutting, welding, any repairs that have to go on prior to doing any coating or additional blasting, make sure that, well, one big one is if you're cutting on anything galvanized. I don't know if anyone's ever put a cutting torch to galvanized coatings before. It's a smell and taste you'll never forget. It's pretty nasty. It's not good for you. So again, please be sure you have the proper PPE. Safety stuff. If it is a known lead primer job, make sure it is labeled accordingly. Anybody see anything goofy here? I hear some chuckling. I don't think barriers make a good pad for an outrigger. It's not often you'll see that kind of thing, but when you do, no, just no. Make sure the contractor fixes that. You can't tell folks what to do all the time, but fall protection, probably a good thing. You've got a snooper basket here and everything. They're nice and handy, but when you're standing on something about 60 feet off the ground on that particular bridge with no harness on or anything, that's the sudden stop is bad. This person here, painting along, these are semi-trailers with tarps draped over the top. Traffic was such that as it came ripping through the corridor on 52 in Rochester, it would cause a blow bubble of sorts. He sat down right where he's at, kind of laid back and was spraying on the bottom, and 3 trucks came through at the same time, tossed him up in the air, and he landed about a foot from the edge of the semi-trailers. Just like that, the guy could have gone for a ride down onto the roadway below. He's not tied off. Please make sure folks are paying attention. It's easy to do when you get in these lifts and tight areas to unhook yourself. Approved products list. I'm sure you all know where to find them, but in case you need the link, here we go. Use only paint from the approved products list. Do not mix paint systems, much less manufacturers. If you get stuff that shows up, it's you know they're supposed to be going with Sherwin-Williams, and the next thing you know, Carboline's there. The 2 paint systems will not jive. It's different chemistry. Do not allow it. New and original containers only. No more than 5 gallons at a shot. If somebody shows up with a 55-gallon drum with a bunch of stuff they said was just from their last job, but it's still good yet, are you going to trust it? You don't know where that's been. You don't know how long it's been sitting. Every manufacturer warranty in the world is void at that point. Data sheets and a technical representative from that particular paint company must be available by phone or something during this process as well. So if you've got a question as to why the paint's behaving badly in the field, you have a phone number you can call and talk to someone who has experience. Little pollution control stuff. focus on the containment within the project and not necessarily rely on recovery systems. So what I mean by that is anything that's coming from within the contained area is known as fugitive dust. There are regulations against it, so it's not just a, well, that doesn't look that bad. It's an EPA thing. And fugitive dust from blasting operations from within the containment are supposed to be collected by a dust collector. So over here, I got better pictures later on, but here's your dust collector. You see the hose, everything sucking from within the containment, but yet they've got these curtains wide open. They had a hard time keeping the machines running. They were plugging up. So they got tired of it, put the machines on the outside, and just figured they'd just throw the sticks in and reach everything from there. Well, we were actually getting phone calls. People driving over the top of Highway 52 thought there was a fire below. There was so much dust in the air. So especially when you got two of these going, it was really throwing it. Pictures never really do it justice, but I drove out there and yeah, it did kind of look like there might be a fire. This is an example of a class 4 containment, picture perfect. The first thing you will notice driving up to one of these, if it is working properly, all these drop cloths look like they're being sucked in just a little bit. So that negative air system on the inside of this place is constantly drawn, and everything around the outsides, the bottom, the drains in the deck, everything is tightly sealed, nothing's getting out. So imagine, well, like I said, that is what you want to see. That's perfection. Again, don't forget the dust collector. So it will probably look like something along these lines. You will see several what we call openings in the baghouse to where they can run lines in from any given direction. If they don't have one of these on site, you need to ask them why. Just what their plan is. So this is just part of it here. Roughly an 18-inch or so hose draws a lot of air when it's really flying. You can get done blasting and sometimes within 15-20 minutes you can walk in there and it's clear as a bell. Perfect. You don't have to run around with a respirator or anything if it's doing its job and it's on site. Paint chips, blast media must be recovered and properly stored. And depending upon your contract, they may or may not have to be tested for hazardous materials. I'll touch more on that. So this particular contractor uses a corrugated steel sheeting, I'll spit it out, to where they have a walking surface underneath the bridge for anything high and elevated. Kind of handy because they're able to go along and vacuum everything up right away. So if it's the kind of thing where if it needs to be, it's supposed to be vacuumed up right away before they start painting. If they've got time, they'll do it. If they are worried about rust back, you can cover it with a 10 mil plastic, but it all has to be covered. Can't have dust getting kicked up from the people walking around and getting all sorts of dust in your fresh paint. I have a better picture of that later. Here's part of a vacuum system. So everything being brought up from the bottom, blown into a 20 or 30 yard roll off, depending upon what they show up with. Covered, so you don't have that fugitive dust thing again. This is a recycler. It uses steel shot as its blast media. This is as close as you can get technology-wise right now to an all-in-one system. This is like the Walmart of painting. So they're able to dump into a hopper with an air compressor, force the blast media through a line, and when it's done on the ground, whatever, vacuuming it up, whatever they have to do, it actually sucks it back up into the machine, cleans it through a multi-stage process, and they're able to use it again. Very loud. You'll notice they're very loud, but they're efficient. We own the blast residue, not the contractor. Goes into our landfills. We have to know where it's at. I will be stressing this probably a few times as we go. Until it's proven otherwise, it is considered hazardous. So, if using steel shot, you won't have a lot of waste. The only waste that you end up with is the rust, the paint chips, anything that is non-ferrous as far as the steel shot itself goes back into the machine, like I said, and then you've got the waste dumps. So this is a typical flyover interstate bridge over, say, I-35. And you've got 7 barrels of waste. Not bad, actually pretty good. But even while it's on site, until you know it's hazardous or not, you gotta have something around it. These folks just had a dog kennel that they haul along with them, a bike cable. You're just keeping the honest people out is what you're doing. For the rarity these days, but it does still happen, they may use a coal slag, like a blast furnace coal slag, as a blast media, blast ox, black diamond, and all of that, every bit of it that comes out of the nozzle gets sucked up and ends up in these roll-offs. You can have just as many roll-offs as you do barrels. So this is one reason we've switched over to using recyclable steel grit, is you don't put near as much material into a landfill, because we fill them up fast enough as it is. As far as their containment goes, in these drums, or the roll-off dumpsters, make sure that the cover doesn't have any rips or tears. Make sure that they don't have a bunch of holes punched in it, you know, just the obvious stuff, right? Do not allow the contractor to mix the waste streams. If they can throw their stuff in it, and we pay to get rid of it, double bonus, right? That's a no. So if you start seeing all kinds of their waste plastics and rope, buckets, steel pails, anything like that, that does not go into the landfill, because that does not go on the waste manifest. That's not painting waste, that is contractor waste. So they do have to keep that separate. Like I said, from the recycling machine, oops, somebody thought it'd be a good idea to just start piling it all in there. It didn't make it through the machine like this. There's no way it made it through the machine. So, just remind them it's got to come out. Now, if you're not sure whether or not your waste is hazardous, a lot of the bridge information that exists out there will state historical record whether or not it's got a lead-based primer. If it does, you already know. You're treating the waste as it's hazardous, not an issue. If it's unknown, or you're just not sure, you can do a TCLP test on the waste you end up sampling. It's a toxicity characteristic leaching procedure. Basically a fancy way of saying, will the lead in the waste leach down into the soil and the groundwater? So you take your samples, package them up, complete a waste manifest. Whatever laboratory you're sending it to will have their own waste manifest, so you can just download a copy of it, fill it out accordingly. If you've got any questions, you can contact me. I've done a few of these. Or even just the lab themselves. If tell them what you need, they will tell you how to complete it properly, and you're off to the races. If it does come back as yes, it's hazardous, please make sure that the folks hauling label it accordingly. That is federal law. Just one little sticker with all that little information on it, and they're bye-bye. So, surface prep, like a lot of things you do, whether it's at home, whether it's at work, the prep is what gives you the first step in good finished product, right? So, solvent cleaning is probably something you're going to see more in newer construction. Like I said, most of this covers field repaints, but you will have things show up out in the field. Like we just a few years back had a bridge built in Red Wing, steel tub girders. So all your fasteners will come with these coatings on the fasteners themselves, whether they're hot dipped or it's a mechanical galvanizing, one or the other. Green is, green's the hot dip, blue is the mechanical. So you're not going to want to sandblast every square inch of these things and rip all this galvanizing off and take away your protection. So you can use a solvent. So MEK was used on this. You won't get 110% perfection, but as long as it looks as a visual representation somewhere in this neighborhood, you'll be in good shape because your primers will bond. So for field repaints, structural steel has to be blast cleaned. You're not going to be able to get away with any sort of solvent cleaning because generally the reason you're repainting them is because they've started to rot out on you. So we blast according to SSPC SP10 or a NACE number 2, which is also known as a near white blast. It doesn't have to be 100% solid white. Zinc rich systems cannot be applied over visually existing corrosion. They will not bond. It won't happen. So it's another reason that we have to do blast cleaning. If you show up on the job and they just getting fired up, start blasting, step out. You don't want to be standing inside. Maybe some of you have been around some sandblasting before, I'm not sure, but they could be running 4 lines at, I think, roughly 150 pounds of line pressure. It will peel the hide right off of you if you get a direct shot from it. So when this starts, just excuse yourself until they're done. Just another example of blasted and a little left over that they're still doing. This is a good example of near white. You will end up with what we call just little shadows. If it's never been repainted before, you may have mill scale. So you may not know what mill scale is.
I'll go with I don't know what mill scale.
Okay, so when steel comes from the foundry, in the cooling process, it forms a thin outer layer, is kind of the rough way of putting it. So when you go to blast that steel, you have to try and get as much of that mill scale off there as well and get back down to the raw steel beneath. So generally what you'll have, these little bit of shadow left over, might be some remnant of that mill scale, but make sure they get all the little nooks and crannies, especially underneath. Let's see. The anchor profile will be something that you check when they're done blasting. There is a spec for 2478 and for 2479. So if they're doing a field repaint and you're going by 2478, you look for a anchor profile of 2 to 4 mils. And what an anchor profile is basically you've got that surface area of your steel, and when you run your hand over it, you feel it's just slightly coarse now. So if you were to magnify that on like a cross section, you've got little peaks and valleys as to what you feel. So you don't want the depth of that to be much more than 4 if at all possible. Or they might really be ripping into the steel. If it's the second time it's getting repainted in the field, it could very easily get up into that range. As I mentioned earlier, the primary system that we're using these days is the recyclable blast. There might still be some use for the black diamond blast docks if your engineer approves it. These might be in spots that are right next to, say, a commercial building. If you're downtown Minneapolis or St. Paul, and you've got a bridge that goes, 100 feet away from a commercial building or something, and they're worried about noise and everything else, they might approve this other system. But for anything in the outlying areas, chances are really good you're going to find the recyclable. So again, lead is hazardous, no matter what anybody tells you. So if it's on the report, it's a pre-existing thing, it is hazardous material. If you need to test it to be sure and you come back with lead, yes, it cannot be shipped any other way. Once blasting operations are completed, you get a chance for everything to clear out. You can go in and take these profile measurements for anchor profile, and depending upon the method used, the blasting residue is likely going to have to be blown down before you will actually get decent measurements. So when the contractor's done blasting, they may need another 20 minutes, half an hour, whatever, just to go rip through that section real quick and just blow everything off the girders. Might be tough checking the bottom flanges and things like that otherwise. This is kind of what I meant by if they need to cover it because they're worried about time. They have a 10 mil poly over on the other side here. This is the picture where they just folded it over because they're actually going to start vacuuming it out. But if they need to get going on the primer because they're worried about things starting to rust back, you can allow them to do this, but they need to go around everything. Another reason we wanted to switch to recyclable. Because they have to. They're not going to paint until they get all of this vacuumed out, because it's got to go through the machine. If it's coated in paint, they can't reuse it, and it's worthless to them at that point. So you'll notice they just got done blasting probably 15 minutes before this, and all of this is already pretty well cleaned up, and they're down here working on the other part. They will have people in there vacuuming grit as they blast, as they get going. And here it is all cleaned up. It's probably one of the cleaner painting environments you'll ever see in your life. It's pretty amazing. Weathering steel in the wrong conditions will rust very rapidly. If part of the job is taking care of some intermittent spots on weathering steel, it's usually beneath your deck joints, joint ends or abutment beam ends, 7 feet out along the beam. That's where you get most of your chloride infiltration. So if you end up having to test for chloride as well, those are good spots to check. Directly below a bridge joint in the deck, at either end, over a pier, whatever have you. Or directly over an interstate lane, because you get a lot of salt spray. So if you need to find a place where you think that might be a good spot to check, that would be one.